Welcome to the Blockchain Security course. Let's proceed and introduce your instructor. My name is Joseph Holbrook, and I'm the owner of a new learning platform called myblockchainexperts.com, and I'm based out of Jacksonville, Florida. I've been a certified Bitcoin professional, a certified blockchain solutions architect, and also an avid blockchain and cryptocurrency geek. I currently have been working in the cloud and blockchain arena for well over a decade. Let's go ahead and proceed on and talk more about blockchain security. The objectives of the course is to help you gain an understanding of why blockchain security is important. We'll proceed and talk about how security in blockchain is approached. We'll then proceed and talk about blockchain technology around security. We'll then discuss different platforms such as Hyperledger Fabric, Ethereum, Corda as well. We'll be discussing the fundamentals. We'll then proceed on and talk about consensus methods. We'll talk about smart contracts and chain code. We'll then proceed and talk about best practices in security. We'll then talk about cryptography and why that's important to understand. We'll then talk about membership in a permission blockchain. We'll then talk about channels and how they provide additional layers of privacy. We'll then proceed on and talk about ledgers and some concerns around security with a distributed ledger. We'll then talk about permissioned or permissionless blockchains at a high level and understand some of the areas of security that we may want to look at. We'll then discuss what a trust or trustless blockchain is as well. We'll then talk about risk assessments and risk mitigation. We'll then proceed and talk about compliance benefits and also requirements. We'll then touch on some of the known vulnerabilities to some of the more common blockchain platforms. We'll talk about vulnerability remediation. We'll talk about Hyperledger Fabric, Ethereum, and Corda blockchain considerations. And then we'll wrap it up with a review of the course. We have a lot to cover, so let's go ahead and get started. Blockchain security fundamentals. Well, let's proceed and talk about some fundamental areas around blockchain security. Before we get started, though, let's do a quick refresher of what exactly a blockchain is. We know that a blockchain is a cryptographically secured, shared, distributed ledger. We also know that generally these transactions are immutable. Once they're written to the blockchain, they're not going anywhere. They're there. They can't be deleted. They don't support generally CRUD capabilities like in a centralized database. It's considered as well transformational technology, and we're seeing a lot of organizations start investing in blockchain technologies. It is decentralized database which stores information in the form of transactions. Now, this is true in the permissionless world. However, when we get into the permission world, things get a little fuzzy. We'll talk more about that and how we have to address that from a security perspective. Let's talk more about blockchain basics before we get into some of the details. We know that a blockchain is doing what? It's essentially writing to a ledger, these services that are running on the blockchain, whether it's on Hyperledger or whether it's on Ethereum, is essentially writing data. It's appending that data to a distributed ledger. We know that we want to compare a blockchain to a book, and in that book, we got to write to the pages which are considered blocks. Every time we write an entry to the book, we consider that a transaction. Let's think of the blockchain as a book that can be written to but not erased. Blockchains can provide private or public capabilities for our users. Blockchains are revolutionary when it comes to trust. We'll talk more about that. One of the facets around blockchains is that they trust the technology, and you as a user, an enterprise, can trust the technology because of the hardware and the software involved. When we consider basics of blockchain, we want to just talk about another definition or another approach to look at it, because we know that in the world of blockchain, there doesn't seem to be one standard definition or two or three. Everyone has their own view. but generally it should be summed up simply as a globally shared data structure. For us into the data services that know data, we know that it's a data structure. We know that it has a specific approach to how these transactions are being written to, how it's being appended to the blockchain. It's basically a back-end database where we're going to call this a ledger. Basically, in the world of permissionless blockchains, everyone can read and write to the blockchain. Essentially, there's visibility. Another word to look at it is it provides transparency. Now, again, we're going to take this another way and talk about permission blockchains as well. That's going to be the focus of the course because most of the folks will be working mainly on permission blockchains, especially in an enterprise. When you come to change anything in the database, you need to create a transaction. You need to submit a transaction. In the world of Hyperledger, we would call that propose a transaction. The word transaction is going to apply a few things. Basically, it's stating, the first thing it's really stating is you as the user want to make an update to some data, whether it is to sell something or to update the ledger with your certification information, whatever the platform is, the goal is to change data. The second goal is to also allow the parties that are involved to be notified of a change as well. That really should be the two main things. When we talk about blockchain and what it is, how it compares to other technology, think about it as a telecom network to a telephone. A database is centralized where the blockchain is decentralized. Blockchains are not built from new technology. So where am I going with this review? We need to appreciate a few things here. It is a syncing of three existing technologies, and each of these technologies maintain distinct concerns around the technology. We'll talk about that here throughout the course. Also, it can be private or public. We already know that. Now, we want to make sure that we understand what these three technologies are. Essentially, we have peer-to-peer networks. So, because it's a network, that brings up a lot of concerns. And we need to realize because it's on a network, we know that there's certain protocols that are being used, like TCP/IP, which are notoriously poor performing, but also extremely vulnerable in a lot of cases. We know that because as a network, we're going to have firewalls to deal with. We're going to have other things such as switches and routers to be concerned with in some cases. Now, we'll talk a lot more about networking coming up. We just want to make sure that you're aware that that's one of the technologies. Second technology is private key encryption. We need to use basically keys to be able to access our key management services or certificate authority. We need to use anything from PKI. We need to use SHA 256 secure certificates. Again, a lot of different protocols there at work to be concerned with. Lastly, it's a program. A program is what? It's using code. Code is certainly vulnerable to hacks and bad programming, not even just intentional. It could be unintentional consequences. So we need to look at our code. Is it written in Python, JavaScript? Is it in .NET? Whatever we're going to develop these smart contracts on, we have to look at it. So if we're looking at Hyperledger, we're looking mainly at Golang, for example. If we're looking at Ethereum, it's going to be Solidity. If we're looking at other blockchains, we need to understand what those smart contract languages are going to be written in, what the dApps are written in as well. Then we also have APIs as part of that to be concerned with. API is essentially an endpoint that you're going to connect to access the blockchain services. Now, digital identity. We need to realize that digital identity is going to take a public and private key and create this identity that you could use to reference who you are and that you're authorized to access the blockchain. This is part of the CA. Every blockchain is going to implement this a little different. This is really more true in the world of permission blockchains. We know that blockchain is revolutionary, and we know, again, as a refresher, that it's not new technology. It's taking older technologies that make sense together now. Trust is at the center. We know that it's a tamper-proof public ledger of value. We know that it's currently very disruptive in a lot of industries such as financial and logistics. And it has numerous use cases. So let's go ahead and talk more about the technology and how security starts playing in here. We know that, again, in the world of permissionless blockchains, things have to be approached differently. We know that this ledger could be on computers, which are nodes distributed throughout the world. Well, because it's distributed among the world, we know that we don't have control over the nodes as an organization. We don't have control over the users or what type of contracts are deployed for that matter as well. We also understand that this should be an immutable record as well. Now, we again realize that it's not a new technology, but what I'm trying to get at here is that we know that these three technologies, networking, basically cryptography, as well as programs, have vulnerabilities. We need to start considering what they are. Now, when it comes to blockchain security, under no circumstances do you approach security in Ethereum the same way that you would approach security in Hyperledger. We need to realize if it's permissionless or permissioned, membership is going to be handled differently, authentication and consensus as well. Endorsement is implemented in most private permission blockchains. We'll talk about Corda. We'll talk about how things are handled in Hyperledger, for example. We know that blockchains are decentralized. That's, of course, in a permissionless blockchain, but in a permissioned, it's more centralized. In other words, it has to be centralized in a lot of cases because why? The enterprise wants to mitigate the chances of someone that shouldn't be on the network being on the network. And to do that, we have to maintain control. We need to analyze our use cases early and frequently. Blockchain security is based mainly in cryptography, and it utilizes this in a decentralized nature that provides the foundation for its security. Essentially, we're trusting the technology. Blockchains are only as secure as the infrastructure. You may have the greatest cryptography algorithm in the world. However, if you have the poorest network configuration that's available and you don't maintain a proper firewall, nor maintain your patch updates for your network services, then your blockchain is only secure as the infrastructure, the weakest link. Once again, you may have great cryptography, great membership control, but if you don't have a secure network, then everything is really game on for the hackers, essentially. Enterprise governance should be defined as well. We need to define how our blockchain services will be overseen by the organization and identify any kind of best practices compliance that needs to be addressed as well. We need to also realize that compliance can vary widely depending on the country that your data is located in, the customer base that you have. We'll talk more about compliance a little bit deeper as well. Now, we need to realize that blockchain security needs to be approached differently in a permission blockchain. We need to be able to prevent anyone from just accessing sensitive information. We needed to deny these attempts to change data, for example. We have to guard our encryption keys. We need to have strict membership. We also need to consider decentralized identity as a way to mitigate issues, for example. Now, when we talk about solutions, we want to discuss hardware and software. Let's talk about hardware first. Now, when we're talking about permissionless blockchains, generally you're going to have a wallet to purchase tokens. And in Ethereum, for example, we need to be able to run a smart contract. And to be able to do that, we need to have what? We need to have gas. Gas is an estimate of what? The amount of compute power, essentially, to run the smart contract on an EVM. If we're dealing with permissionless, we need to look at hardware wallets for our users. If we're not looking at essentially permissionless blockchains, then having a wallet is not needed because we're not basically using cryptocurrency or hardware or tokens, like in the case of Ethereum. When it comes to software solutions, we want to consider, of course, our cryptographic algorithms, our digital signatures, hashing functions as well. And again, we also will want to implement a MSP, like a membership services provider. Many different ways to approach that depending on our blockchain of choice. We need to also consider a few other things like the smart contract quality, how well the smart contract has been tested and validated. We need to validate not only the smart contract coding, but the data quality. Is it possible we could be using bad data, for example? Are we also looking at possibly having network disruptions that can also provide instability in our blockchain? Is it possible our keys could get stolen? What about performance being hindered? And then what about the vendor platform that we're running our services on? These are just some of the main concerns to think about. Now, when it comes to risks in our blockchain, there's a wide area of concerns that we want to consider. We want to, of course, first consider our network security risks. This could be our firewall. This could be our network protocols that we use. This could also be access to the network. Could also be our directory services, depending on how we design our network. The poor design of the blockchain itself could be a factor. API exposure and vulnerabilities that could go with it. We also have to realize that our membership provider could have vulnerabilities as well. We need to consider key management and how we handle our keys as well. Now, malware and viruses can certainly happen. We need to look at those. We're going to be talking more about malware and viruses more in detail throughout the course. And attacks that can happen, such as a 51% attack, and also too, a DDoS attack can also occur on some of the blockchains as well. Now, when it comes to best practices, again, we'll talk a lot more about this, but we want to really consider having smart contract code audits. We want to have DevOps in place. We want to look at due diligence for our code base. Now, I just want to point out one thing about DevOps. DevOps, again, is an interesting process, and it needs to be applied with a little bit of different care than what you would normally do if you're deploying typical software. However, DevOps can certainly work in the blockchain world, and I'll discuss more about that in the upcoming lectures. Now, due diligence. We need to realize that our code base may very well be public code base. And in most cases, it's secure, it's been well tested, but we need to pay attention to the code base that we use. Again, there could be vulnerabilities just waiting in wait for an opportunity to come out, really. Now, we need to look at our API and endpoint management. Now, an endpoint is essentially what? It's an on-ramp to the blockchain service. For example, in Hyperledger, we would be considering our BNA configuration, for example. We'd also be looking at the client RPCs as well with our APIs, not only in Hyperledger, but in Corda, for example, as well. Now, we need to do assessments and remediate based on those assessments. We have to have training, right? If we don't have training for our blockchain users, then we shouldn't expect them to have an idea how to handle things, what to look for, how to behave. We also need to consider integration of blockchain to the enterprise services. Now, when we talk about integration, we could be looking at many different factors here. For example, if we're trying to use a platform that's Hyperledger based and we want to do an off-chain to a third-party service, or we want to off-chain to enterprise services, and this can be done via what's called an oracle, then we need to consider not only our API connections, but the language that we develop in. And also, we need to consider access control, how we sanitize the inputs as well to our API interfaces. A lot more here to talk about. We're just getting started. So let's go ahead and move on to the next module. Blockchain consensus. When it comes to blockchains and how consensus is reached, it's really important to understand that each of the different blockchains out there on the market, whether they're enterprise or not, have different approaches to consensus. Now, some have mining, some do not. The reality is that if it's an enterprise platform, it probably doesn't have mining. But we do want to understand what mining is, especially in the case if we do choose to use Ethereum and understand some of the vulnerabilities that could be exploited around Ethereum, for example. Now, we want to do a quick review of some of the consensus methods in case you may not be aware of that. So let's talk about mining first. So what is mining? Well, mining is essentially a process that's used to add to the ledger. Now, basically, the nodes, the miners on the blockchain, are basically racing or competing to write to the blockchain. And if they're the first to win, then they essentially will get rewarded for their hard work. Basically, mining in Bitcoin or Ethereum is basically based on a proof of work algorithm. Now, mining, again, is called mining mainly because it requires computers to do really hard work. And the comparison is that it's sort of like, you going out and digging up the ground to get your resources. And again, that's a lot of work to do that. Now, when it comes to compute power, you have to be able to have really solid ASICs to be able to do that now in the world of Bitcoin, for example. But with that said, we need to realize too that because the computers that are on the network, there could be, hundreds or thousands depending on the state of the blockchain. For example, like with Bitcoin and Ethereum, the mining pools that were there a year ago, probably 30% are gone now because of the devaluation of the cryptocurrencies. Now, when it comes to exerting, what they're talking about here basically is this. Basically, if you have high-end compute power with an ASIC, a TPU, whatever you're doing when it comes to computers, but let's just talk about mining. Basically, the node that is on the blockchain is competing to write that block of transactions to the blockchain. Now, there can only be one winner to basically get a mining reward. And that's basically based on a transaction. So basically, one miner will get rewarded for, getting there first for solving the mathematical computational challenges. And again, only one can really win. With that said, we just want to realize that mining is considered hard work. Now, a reward is given when a block is discovered. The discoverer essentially can also get a certain number of Bitcoins as long as it's agreed upon, by everyone in the network, essentially. And that's why mining was really profitable for a while there, because again, if you were getting Bitcoin one day and it's, $3,000 a Bitcoin and you get 2 Bitcoin for mining, let's say, one transaction, that's a pretty good return. But if it's taking you 3 weeks to get 1 Bitcoin and your power bill is, significant, then that might not be that significant overall if you're getting just one transaction, basically, or one reward basically given to you every couple weeks. That's not profitable. Now, there's bounties in Bitcoin. Basically, every 210,000 blocks, that reward is cut in half. The miners are awarded fees as well. So when they're participating in a transaction, they do get a small amount of Bitcoin as well. So they don't have to always be the winner when it comes to a transaction to write to the blockchain, but if they're participating in the transaction, they do also get transaction fees. Small amount, but it is a fee. So it does provide an incentive to the miner to basically add that to their work that they're doing. When it comes to algorithms, basically the common ones are proof of work, proof of stake, DPoS, BFT, and DAGs. Now, we'll talk about each of these, but there's certainly a lot more. And when we get to the individual blockchains, we'll talk more about how that all comes into play. But basically, at a high level, we want to make sure that you're aware of some of the algorithms out there, and also be aware that each of these could pose a different set of threats as well in their own way. Proof of work was the first blockchain consensus algorithm. This was essentially released by Satoshi Nakamoto. He created the Bitcoin blockchain. Now, Satoshi, again, we don't know who he is, if it's a he or a she really, nor do we know if it's actually an individual or, an agency or whoever did this, right? So that's the thing. No one knows who this person is. He sort of disappeared off the map. But, he was really the one that basically has credit for creating Bitcoin. Proof of work miners solve hard problems to create blocks. Proof of work runs on a system of the longest chain wins. Essentially, it's like running a marathon. Whoever runs the farthest, the quickest, basically wins the contest. It is very expensive, though, to be a miner in the sense that you have to have very expensive computer equipment. You need to have ASICs, real specialized equipment to be able to mine Bitcoin profitably. Now, also, the power to run these computer rigs is fairly substantial. It's not like running a laptop. Now, proof of stake is different, and I like to compare proof of stake to sort of like betting or wagering to basically like a horse race, sort of similar to that, where you're betting that this horse is going to win. Again, each of the blockchains that support proof of stake support a little differently, but in general, there isn't miners, they're basically stakers is another term to look at it. Now, when it comes to proof of stake, again, it could be easier to attack as well. But basically, one of the challenges around proof of stake is just, again, trying to maintain some kind of integrity as well. But the positive side of proof of stake, though, is that it uses less power as well. Okay, now let's talk about DPoS. So DPoS is basically a hybrid in the sense that it has some benefits to proof of stake, but not everyone. Now in DPoS, miners can collaborate to make blocks instead of competing like you would do in proof of work or proof of stake. Basically, this is sort of like what I would call teamwork. Instead of like each of the mining nodes working individually, this is where collaboration is sort of brought into the algorithm. The benefits of this is that it's cheaper transactions and faster, but one of the downsides to this is that it's more centralized. Examples of that would be Steemit in the US. Now, Byzantine fault tolerance, this is basically where you have a traditional problem in distributed computing. And this is really where you have, for example, let's say generals surrounding a castle or a city, and you have 5 generals. And in the old days, what would have to happen is how do you actually handle communication between, let's say, 5 generals before there was radio equipment or anything? So one of the challenges was how do you time like an attack so that all the 5 generals in that surrounding area knows when to attack at what time? And again, one of the challenges is what happens if you send out a messenger and that messenger is attacked, or the message is basically intercepted. Then what can happen is that the attack on the castle may not be efficient or will work out. That's considered the Byzantine fault tolerance question, and that's historically from a perspective of what BFT is. But basically, in computers, we look at it as a distributed computing issue where you have multiple nodes, and the nodes essentially need to be coordinated to be able to have the network operate appropriately. Now, what is the challenge in a network where you have distributed nodes? Well, you have latency. That, again, if you have nodes too far away, then that transaction, especially in a SQL-based transaction or relational database, then you need to make sure that that transaction can be committed in a timely manner. Now, when it comes to PBFT, it does, again, address issues around basically BFT. It is very efficient. It has high transaction throughput, but it is centralized and permission-based as well. Now, the common blockchains that use a form of BFT, Hyperledger, Ripple, and Stellar are good examples. And then we have DAGs. Now, a DAG is a directed acyclic graph. This is really not a blockchain. It's more of a distributed ledger in the sense that consensus is going to use what would be more of and again, a data structure is really the best way to look at it. It's going to address a data structure in a different approach. Instead of like being synchronous, it's really going to be asynchronous. Because you have basically what's called a DAG, then you have these transactions that are distributed in different manners, and this helps increase the performance of that ledger essentially. Now, examples of that would be IOTA and Hashgraph. Let's go ahead and move on to the next. Let's talk about smart contracts. Now, when we hear the term smart contract, we want to be aware that, first of all, it's a term that is used to describe some kind of computer code that is going to execute some specific functions around some kind of an agreement that was set up. Now, let's clarify two things. A smart contract is neither smart nor is it a contract. That's one of the challenges that I run into every day training and talking to customers, is because sometimes smart contracts infer that there is a legal agreement there. Now, can there be legal pros? Absolutely. It just depends on the blockchain and how things are implemented. But when it comes to platforms like Ethereum, a smart contract really is not going to be legally enforceable. So let's think of it from that perspective. We'll talk more about it, but I want to just start off with that. Now, the process is automated and can act as a complement or substitute for legal contracts. Now, this is, again, really going to depend on the blockchain and the end users. The terms of the smart contract are recorded in computer language as a set of instructions. Now, when we talk about smart contracts, in most blockchains, we call a smart contract a smart contract. In the world of Hyperledger, for example, we call it chain code. When it comes to smart contracts, essentially they provide autonomy, the ability to put something in computer code and let it basically execute on its own when the conditions are met. Trust. We trust the code to do what it's supposed to do because it's coded in to only do one thing. It's not going to make decisions. We're not talking about some kind of manual effort that a mistake can happen with. A backup, basically when we deploy smart contracts, these are deployed on every node that we're deploying the smart contract on in most blockchains. So for example, when you deploy in Ethereum, it's running on the EVMs. When you deploy in Hyperledger, you have to install the chain code on the nodes that you want to run the smart contracts on. Safety, once again, it's not going to do anything that it can't do. It's just not going to happen. They're fast, it's automated, and there could be savings that are realized as well when it comes to smart contracts, especially if you're able to create processes that had intermediaries, and then you're able to remove those intermediaries. And then accuracy. If you program your code to do one thing and it can only do one thing, it's not going to do the wrong thing or anything. So you don't have to worry about that. Plus, if you remove the manual labor, the typing or anything that a human can do, then you reduce the chances of errors. When it comes to smart contracts, when we compare a contract to a smart contract, a traditional contract is different in the sense that this is the way business has been done for years and years. Go out and get an attorney, draw up paperwork, you basically submit whatever you need to meet the contract. If you're selling something, provide the funds, whatever that requirement is. Usually you need to have a physical presence, you have to sign the paperwork, you have to have an attorney. Again, that's your traditional contract. Smart contracts are basically going to execute quicker. They're not going to have any kind of manual labor in the sense. And again, they could be somewhat cost effective as well. When it comes to smart contracts, they define the rules and penalties around an agreement in the same way a traditional contract does. They can also enforce these obligations. Now, enforce isn't, we're going to go file a lawsuit against you. It's more like it's not going to execute if you don't meet the requirements. That's really what it's saying. Smart contracts can make up a DApp. Basically, a smart contract by itself will only do one function. For you to create an application that's going to do several things or something useful, you need to create what's called a DApp. That's a distributed application. That's going to be 2 or more smart contracts. When it comes to smart contracts, they provide security that is better than traditional contracts because of the fact that it can only do one thing. You can't just go in, for example, in Ethereum, you can't just modify as a user a smart contract. This has to be done via the code. So it's a little bit more to what people think you can actually modify. You can't. Now, we know that smart contracts, can be vulnerable, and I'll talk about some of the smart contract vulnerabilities coming up. But basically, a smart contract, again, is really meant to cut costs. On Ethereum, they run on the EVM, and then we know a DApp is going to be running on Ethereum as well, but these DApps are complex smart contracts. When it comes to functions of a smart contract, there's 2 functions typically in a smart contract. In most blockchains, we have a constructor function and a fallback function. The constructor function is going to be sort of similar to an init, initialization. Now, like in Hyperledger, things are a little different in the sense that you're going to have to call separate functions and they're a little different. We'll talk about that in the Hyperledger section. But basically, just realize that at a high level, you have to have some kind of a constructor function and a fallback function. And Hyperledger does have both. It just terminology is going to be a little different and things are handled differently. But Ethereum is very similar to this. Now, when it comes to the constructor function, we want to be aware that this is going to kick things off. This is like the deployment phase. The fallback function basically is going to be a function that hasn't really been defined. In other words, what will happen is if you try to send Ether to an address and you send it to the wrong address, then it should be rejected. Again, if you send it to the smart contract, for example, it will be rejected. Now, if you send Ether to the wrong wallet, then you're out of luck. So just be aware of that as well. Now, let's talk about, for example, in smart contracts. For example, you can run into challenges with smart contracts around how you have a return value issue, like programming a low-level function. You can have failures that can throw an error. We'll talk somewhat more about these and how functions can be actually vulnerable. When it comes to enforcement of a smart contract, we want to be aware that Ethereum, for example, states that all modifications to a contract's data must be performed by the code. In other words, you as a user can't actually directly modify it. Modification of a contract's data requires a blockchain user to send requests to its code. In other words, you got to go ahead and do this in a proper order. You then basically send a request. That request is received. It's going to kick off a basically initialization process, and also will check permissions, etc., to see if that can be allowed or not. Now, one more thing about modifications. For example, with a modification, you can actually have certain parameters change, but keep in mind that once the contract is in the blockchain, it's essentially final and it can't be changed. Now, there are parameters that can be changed if that's allowed with the original code that's used. Basically, one of the things to think about, your developers will of course want to pay attention to this, is perhaps create a versioning system for your smart contracts. To do that, you want to pay attention to the code that you're using, the Solidity version you're using, also to the Ethereum version, the release basically. These are handled very differently in each blockchain. For example, even in Ethereum, for example, the way things are going to be handled in Homestead is going to be different than in Constantine. And these are some challenges, I think, that can take some time to really determine what is going to be the best approach for your enterprise. But with that said, if you do want to update your smart contracts, version them in a manner that makes sense, you could also create like a name registry as well. That's been seen before. But with that said, you may just have to pay attention to how you logically code and also to the code that's in your library as well. With that said, there's a lot more to, of course, smart contracts. It's more of a development discussion than anything. But basically, a traditional database is going to enforce a stored procedure. This is, again, predefined rules. And essentially, smart contracts are doing what? They're just essentially, basically running what's been defined. Basically, it's predefined. When it comes to enforcement, one of the things to think about is that, again, we know that if we have to modify anything to the contract's data, the code has to do it. And as long as it's authorized by the code, and remember, it depends on the type of code we're looking at. We have a lot of other things to consider. We need to look at, for example, the compiler versions, the memory layout, the contract's initialization, the functions, the proxies that are used, the Ethereum internals, for example, when we talk about Ethereum. There's a whole laundry list of basically development-related challenges to address with smart contracts. But what I'm trying to get at here is it's not exactly something you can do with the smart contract easily to modify it. You want to version it. You want to pay attention to your releases. Modification of the data, you have to send the request to the code. It kicks off a process. And if it's able to compile, great. If it can't, it won't. When it comes to smart contracts and legal enforcement, we have to realize that because something is called a smart contract does not mean it is legally enforceable. A lot has to do with jurisdictions, the way the language is written, and also too, computer code doesn't really translate well to legal jargon, and therefore you need to consider an approach such as a legal prose approach, as in Corda, to accommodate this. Could be used as evidence, that is. And we want to think about this as a vending machine. Essentially, if we go to a vending machine and we put in the amount of money that we need to get that drink, if it's $2, it'll release that drink. If we don't, then it won't release that drink. It's pretty much what it's saying. For example, Corda, we know, supports legal prose. When it comes to a smart contract workflow, we want to be aware that smart contracts will be predefined. We have to define the structure of our smart contracts. And when we say predefined, what does that mean? We have to, of course, determine our functions, the initialization process. We also need to look at variables. We need to consider how much memory it's going to use. There's a lot of things that go into this. Now, we need to have a trigger event and how that trigger event is received. Essentially, if someone drops an Ether into your wallet, then it will trigger an event to send off an email to say thank you for donating to my Ethereum wallet. Now, are things that easy to do? Not really, because we know that in Ethereum wallet, we don't know how to address, for example, easily from a recipient perspective, who's sending us what. So we need to tie in some additional code to help identify who is sending us like Ethereum funds, for example, like the from wallet address, and how do you identify the from, for example. So there's a lot more to that. So we need a trigger event. Whatever that is, we need to identify it. If that trigger event is going to, for example, trigger based on a deposit or transfer of title, it will then execute and transfer what it needs to transfer. And then once, let's say, the funds are received, the settlement will occur and that transaction will be fully consummated from a recipient and a sender perspective. Now let's talk about some vulnerabilities. The first is access control. This is generally where permissions are involved. And if you're a developer and you give public access to everyone to your smart contract, again, you're not limiting access. If you don't assign the proper code control, that's on you, of course. So with that said, we're going to talk more about remedies for these in the vulnerability remediation part of the course. The next one is arithmetic. This is where, for example, you code your smart contract and you have an overflow or an underflow. This is generally going to happen with a cryptocurrency-based contract that you're trying to update balances. Is it possible someone can create a wraparound or cause an issue that that might affect the results or the output? Absolutely. We'll talk more about that in the upcoming section. Return value is basically where a value is not checked properly and it's throwing an error. Reentrancy is an interesting one because what this does is essentially creates a double spend where this is really initiated by a withdraw function in a smart contract, and this results in a situation where the fallback function is called, and because it's called, it's possible to withdraw the amount twice if the smart contract isn't updated in time. With that said, it's a common issue if you're not paying attention in the cryptocurrency world. Now, a DOS attack is exactly what it sounds like, a denial of service. This is where a smart contract can be rendered essentially useless by having basically a DOS attack basically implemented upon it. And that's usually done because of loops or what's called a recursion. We'll talk more about that as well in the upcoming modules. Bad randomness. This is generally a result of getting random numbers and not handling them appropriately. Race conditions. Now, a race condition is essentially what it sounds like. This is where you have essentially a task going on, and because the task is going on, you have typically several programs competing against each other. We'll go ahead and talk more about that as well. And then a short address is again a common issue as well. If you're not paying attention, it's a function issue. And then a timestamp dependence. This is again based on, for example, if you have a smart contract being designed and you create this at a specific time and the smart contract has a timing issue, specifically around block timestamps, this can come up as well. We will talk more about that in the later modules. When it comes to deploying
any kind of software or code, it's important to understand what are some of the best practices that go along with deploying code, for example. Let's talk about some of the areas that you'd want to consider around deploying smart contracts or any kind of blockchain-related service. When it comes to best practices, these, of course, will revolve around the development of your smart contracts. This is, again, where most of the work will come in determining what you need to deploy, when you have to deploy it, how do you modify facets around your smart contracts. And we already know that that's not that simple. So we have to consider best practices for smart contracts. We then want to look at our wallets as well. How do we manage our crypto wallets if we're using anything that is requiring tokens or cryptocurrencies such as Ethereum? We need to also understand any kind of best practices for blockchain deployments. For example, how do we deploy a blockchain and integrate it with our enterprise environments? What do we need to consider? One of the first things we want to consider is anytime we're deploying any kind of software is to have some kind of a best practice around software development. Now, when it comes to software development, usually you would see software development life cycles implemented. This could be agile and iterative format or waterfall, spiral, several others as well. Again, there's no real documented best practice per se for you as a developer to pick one over another in most cases. It really depends on your environment and how well you want to collaborate perhaps with other folks in your environment. But also too, what are your current testing formats that you're using? When you're looking at SDLC, basically the goal is to provide high quality software. Once again, try to do it right the first time to save money. Now, DevOps is, of course, a term that's widely used in IT right now. This is essentially a collaboration between development and operations. Basically, DevOps is really taking your agile, but also your lean processes as well, and enabling what hopefully should be full collaboration between your IT departments, such as development and operations. Now, DevOps could also include QA or test. It doesn't have to be just ops and dev. It all depends on your environment. Blockchain and DevOps can provide benefits to the organization. Now, most of the benefits will be provided around how smart contracts are going to be audited, for example. We want to understand our audit policies. We also want to make sure that when we deploy our smart contracts, that we try to minimize any kind of what's called typically source code overflow, where we're not actually doing proper testing code maintenance. For example, you may want to set up a GitHub or some kind of repository for your development, your production, your tests, and QA to make sure things are in order. Have a versioning system in place. And then when we consider smart contract releases, we want to have a release cycle. We want to make sure that we have a proper schedule. We don't want to churn our code. We don't want to make mistakes. We also want to make sure that we deploy our code on the right network. Once again, it's common to want to test as quickly as possible, but you don't want to test in the wrong manner. When it comes to source code too, look at how you validate your source code. Make sure you use a validator tool, for example. Do ensure that you follow the best practices for that blockchain development. Now, if you're using Ethereum, there's a lot of documentation out there. For example, and this is just one example that you could consider for your source code with Ethereum, is to use what's called a bytecode validator. If you go to the link there, it'll bring you over to what's called the Ether bytecode verifier. This will, again, look at your source code and help you validate that you actually have the proper outputs that are required. Auditing. Now, audits are a necessary part of deploying code, deploying smart contracts. We need to have audits, and we need to perform these audits in a responsible manner. Generally, you'll have auditors come in and look at your structures that you have in place, look at your logging, look at your source code management, whatever you're looking at in your enterprise to have audited. Auditors, of course, need to have a proper structure to review. And to pass audits, you need to, of course, follow those structures. So have what's called an expert code analysis. Basically, this is where you're going to go out and have someone come in and look at your code to actually analyze the performance, for example. And of course, you do want to have someone that's knowledgeable do that. You may want to look at a flow analysis. This is where you may want to generate basically a graph or a structure of your control flows. Look for anomalies. Code analysis. Now, this could be, of course, manual or dynamic. Again, you're looking at the line of code to determine how the performance will be. This is, again, typically, if you're going to do this, have someone knowledgeable and very experienced to do this. One of the things that generally can happen is that if you have a developer code, they can become tired. They can just glance over things that, clearly they know what they're doing. They're very knowledgeable and very good. It's just that sometimes mistakes can happen because they have basically that posture that they've been using developing the code, and it just sort of affects their concentration or thought, and they can miss stuff. So have someone else come in, look at the code line by line, analyze it, and basically have someone, with a fresh set of eyes look at it. Vulnerability scanning. This is where you're looking at the vulnerabilities that are out there and sort of validating, do you have this issue or not? Taint analysis is essentially when variables basically could be out of sync. Basically, these variables may execute improperly, so validate that that's not an issue. Now, test coverage basically will validate that the test will cover the whole smart contract. Because one of the things that could happen is that you're testing, for example, your validation program may only test part of your smart contract. Again, that might not be any good if you don't test the whole smart contract. Let's go ahead and move on to the next module.
Cryptography and certificates. Let's discuss why cryptography and certificates are important. Now, first, we need to understand that cryptography is really the practice of sending secure messages. And basically, this is done via encryption and decryption with essentially a set of keys. Now, generally, we're going to use public key encryption in the world of blockchain. We want to, of course, use the public key to essentially use with the private key. Basically, anyone with the private key can decrypt messages and then generate signatures on the user's behalf as well. So one of the things to think about too when it comes to cryptography and key management is to, of course, protect your keys.
When we get to the CIA triad here, we need to realize that cryptography is really part of the overall scheme of protecting your data. Now, generally, the CIA triad is fairly well known in the IT security world. Basically, it has three facets. We have to have confidentiality, we need integrity, and we need authentication. And to do that, we need to have some way to send messages, to save messages, and to protect our data as well. With that said, the CIA triad. Cryptography, when it comes to blockchain and also IT security, we want to think about the fact that blockchain should be essentially non-reputable. In other words, immutable is another way to look at it. Basically, non-repudiation and immutability can have characteristics that are similar, but basically non-repudiation is where someone sends something and they can't take it back. Now, transactions, when they're written, cannot be deleted. So whether or not that user is happy or not with what they said, it's not being deleted. It's immutable. Once again, the two terms that you generally will run into will be non-repudiation and immutability. When it comes to encryption and decryption, we want to be aware of some terminology. The first is encryption, is where we take our data and we turn it into ciphertext. Now, decryption is where we're going to take our ciphertext and turn it into plain text. Basically, in a nutshell, it's really that simple. Think about it as you're taking a message that you can read, and then you're encrypting it with PKI to something you can't read or make sense out of. And then after that, when you want to have it opened by the receiver, they're going to do what? Use their keys to do what? De-encrypt. And that turns it into plain text. When it comes to a workflow of cryptography, we want to be aware that we're going to have plain text, we're going to have it encrypted, we're going to have it turn into ciphertext essentially as part of the process. It'll be de-encrypted, and then it'll be plain text again. Certificates. Now, as part of this process, we need to have some kind of certificate, basically keys, basically stating that here's the format that we're using, here's the certificates that will be used, here is the certificate revocation list. Now, the revocation list is basically going to be a list of certificates that aren't valid anymore. And then we need to also consider our algorithms as well. For example, both Corda and Hyperledger both use X509 certificates in their identity management structure. When it comes to certificates, we need to have these to identify that the sender and the receiver are actually the correct people that should be sending and receiving messages. These essentially act as secure identifiers. The certificate is tied essentially to a public key value, which is then associated with that specific certificate. Now, hashing. Hashing is going to be done because it's part of being able to have that message basically turned into randomness, essentially. Basically, when we look at hashing, it's a way to provide a unique output based on a unique input. Basically, the same data will always map to the same hash. Sort of the way to consider that.
Now, I do have a hashing demo at the end of the course in the demo section for those that are interested. Certificate authority, what is that? Well, we need to have some kind of a control system for our certificates and to manage certificates appropriately. For example, if we're going to have membership and users, we need to have a way to provide authorization to our user base and also identify essentially as well. And a specific certificate will allow us to basically identify who is accessing our system, basically who is authorized. Now, in some of the blockchains, like this is, for example, in Hyperledger, a specific client application or an individual may have several certs, not just one. For example, in Hyperledger, you have E-certs and T-certs. Basically, the E-cert is going to allow you to be a member of the blockchain, and then the T-certs are going to allow you to perform transactions. Each T-cert is basically one transaction. That's pretty much what it looks like, right? Now, certificate authority, we need to understand that we need to use certificates that are going to be standard in the industry, that are going to meet the requirements. There's also extensions on how the certificates are going to be referencing the key identifiers, for example. And when it comes to some of the key extensions that you need to be concerned with, again, we're not going to cover all of these, but just more of a touch and go. We want to just be aware that there's extensions that we need to understand as part of a certificate authority. Let's go ahead and move on to the next module. Let's talk about membership and how membership is actually a very important part of a permissioned blockchain. When we consider membership, we want to think about it as usually a portfolio of services that are being provided by this essentially node in some cases, by this third-party tool you could be using, whatever the tool is, then you need to realize that this should be providing identity, privacy, and confidentiality to your blockchain network. Now, when it comes to membership, some blockchains have a membership service provider. For example, in the world of Hyperledger is pretty common. And we also need to realize that as part of access control, our enterprise or your customer's enterprise needs to be able to restrict and permission the blockchain on an appropriate manner for their services that they're deploying on it, for the risks that they have, whatever the situation is. But basically, your access control should have, of course, some kind of identity management. It should also have a way to handle permissioning along with that, and also should be able to have some kind of an ability to process and handle appropriately attacks as well against it. So if you're using access control in a typical blockchain like Hyperledger, you're going to typically be using an MSP as you would call it. Now, can you swap out the MSP for what you'd like to use? You can if you can integrate it. That's great. More than welcome to do that. But basically, you want to be able to ensure that the MSP has control over blockchain permissions, essentially. That essentially it's going to ensure that data isn't removed. It's going to ensure that data
is not going to exploit the blockchain services. When it comes to membership in Hyperledger Fabric, we of course want to look at the certificate authority. The certificate authority is part of the MSP, but basically it's going to provide registration of identities. It can also connect to LDAP as well. It can also issue the certificates, and these certificates are eCerts and T-certs, for example. When it comes to the Fabric Certificate Administrator, it also provides additional features as well. Basically, it has an HSM, hardware security module, supports specific protocols as well. And we also need to have an endorsement policy. This is going to allow us to ensure that our transactions are going to meet the requirements that we said. If we need 2 nodes or 4 nodes, we need to be able to enforce that, and that's done via endorsement policy. Basically, the endorsement policy is going to look at the transactions that have been submitted, that are proposed. Basically, it's going to validate, does it have enough nodes, enough votes to validate or actually accept that transaction. When it comes to an endorsement policy, for example, you can take these policies and set parameters around them. You could specify what types of transactions to accept and by who. You could also add policies dynamically. Now, we'll talk more about this in further lessons, especially around how to mitigate vulnerabilities with transactions. Now, this is an example on the right about how an endorsement policy could look in Hyperledger format. It's basically in YAML here. And again, that's just one example. When it comes to membership, we need to, of course, have a structure. Hyperledger Fabric, for example, has a very strict structure. Corda as well has a very strict structure. Again, you need to have your MSP, your HSM. You need to have the certificate authority. You need to have nodes in your blockchain. Now, you could certainly set this up. You could have one node handle many jobs or one node do one job. It's really up to you. And that's going to be based on the performance, the scalability that you may need as well, your budget, whatever that is. With that said, we can go ahead and move on to the next module. Let's talk about channels and what they are and why they're important, especially around blockchain security and more specifically privacy. We want to have channels in our blockchain services to help us basically communicate or send transactions in a private and confidential manner. Generally on a blockchain that is not built for having channels, then what would happen is if we make a transaction, then that transaction will be essentially propagated to every node on the blockchain, and therefore everyone else is going to know about it. But what about if you didn't want everyone else to know that this transaction is going on? What about if your competitors are on the same blockchain as you? How do you handle that? Channels serve that purpose. They provide security and privacy. Now, these, of course, can be implemented differently in different blockchains. Corda and Hyperledger do offer channels, and they have some similarities, but they also have differences. For example, in Hyperledger, the channel's defined by each component in the network, and then you have what's called an anchor peer per member, and you also have a ledger, a chain code application, and also OSNs in the channel. So Think of a channel as essentially a little sandbox in a blockchain. Now, the transactions that occur in the channel are only kept on the nodes and available for the members in that channel only. Channels allow any customer, participant, or vendor to have their own ledger on the blockchain. Each of the parties participating need to be authorized to transact on the channel. Members can participate on multiple Hyperledger blockchain networks. We also want to realize that transactions, again, can be utilized in a private manner, and we want to do that via which way? A channel. Now, channels are essentially a way to partition your blockchain. We can consider it a sandbox. We can consider it a way to minimize visibility to others on the blockchain service. In Hyperledger, we can deploy chain code on multiple channels. That's pretty much the way you'd want to approach it. And again, we then would have a Genesis block as well as part of the ledger on that channel. When it comes to channels, we want to realize that peers are connected to the channel, and any peers connected to the channel can receive the transactions that are broadcasted on that channel. Consensus takes place within a channel by the members of the channel only. So if you have 4 nodes on the channel, but you have 30 in your blockchain, only those 8 nodes or 4 nodes, whatever the division is that you're using for your channels, only those members can see or hear what's going on and can participate in the ledger activity. When it comes to creating channels, we want to think about a few other things that are typically referenced in the blockchain world. We have what's called a side chain. Now, a side chain can be a separate blockchain instance that is going to be attached to the main chain, but also can be utilized to perform essentially what's called a hold or a peg. Basically, a side chain is going to be used to typically go off the main chain to another chain. Now, this is something that might be used in the financial sector to provide segmentation of blockchain services. Now, a state channel is going to typically be used to provide a form of off-chain to a payment gateway in some cases. This is also called basically side chaining in some cases as well, depends on the blockchain. Once again, a lot of terminology out there, and sometimes the terminology is just used differently, but it can be the same thing. Let's go ahead and move on. Identity and access management. Now, in a permission blockchain, we of course need to have some way to validate and identify who is who for various reasons. Some of those reasons could certainly be around to challenging your participants to validate that they are who they are. We may also have to deal with know your customer requirements, anti-money laundering requirements, other compliance requirements, and then of course we probably want to have reporting. With IAM, it's really an approach to permissioning essentially, and the goal is to provide enrollment certificates. And this is true in a lot of blockchain platforms, and Hyperledger is an example as well. Basically, being able to be permissioned to access the blockchain and identify who is performing what transactions is, of course, something that most enterprises would want to do. With IAM, the goal is to provide identity management, maintain the participants. For example, in a Hyperledger, it's essentially mapping of LDAP in your user registry to essentially the certs, the T certs, for example, and the transaction ID or the transaction ID.
for the sake of tracing. This helps you identify who your customer is. And of course, this is a big deal in the financial sector. Let's go ahead and move on. Permission or permissionless blockchains. Now, when it comes to blockchains, we know that some are public, some are private, some are permissioned, some are permissionless. But basically, public blockchains are usually referred to as permissionless blockchains or open blockchains. Bitcoin was the original permissionless blockchain. Transactions are processed by all the nodes in the blockchain, and transactions are publicly viewable. So if you're looking for privacy or some kind of security, then probably public blockchains are not the way to go. Now, when it comes to a public blockchain, a couple things to point out is that it is open to the public. This, of course, can expose your organization to unknown participants, to also other vulnerabilities that the blockchain could be subjected to. So generally, we don't see enterprises use an open blockchain unless if it's going to be an off-chain approach for some kind of off-chain transaction. Not always the case, but generally in most cases. Now, generally we would see Ethereum be used for development and create essentially a token that is used for development purposes. But once again, generally you want to stay away from open blockchains as an enterprise. When it comes to public blockchains, there's benefits to that. It's open read and write. The ledger is distributed and it is censorship resistant. It isn't centralized. Generally, it's considered more secure because of the 51% rule. Some of the examples are Bitcoin, Ethereum, Monero, EOS. Now, private blockchains basically refer to permissioned or enterprise blockchains. These are usually open source, consortium, or privately developed as well. Transactions are going to be processed by select nodes in the blockchain in most cases. Transactions are not publicly viewable. Now, that's the public. That doesn't mean that they're not viewable to any of the authorized participants in the blockchain. Now, as far as a private blockchain, again, this is usually going to be permissioned. It's typically a consortium-based as well. The consortium-based blockchains are Hyperledger, R3 Corda, for example. And generally, the consortium members that are using these types of blockchains have interests and have provided some kind of support or some kind of financial guidance or technical guidance to help facilitate some of the features and functions of the consortium blockchain. For example, with Corda, you had several organizations get together initially to start developing a blockchain service. Hyperledger, again, has consortium members. There's over 200 members, at least at the time of writing. When it comes to private blockchains, again, we know that they're private. It's a consortium blockchain as well, and typically permissioned in most cases. Now, can you deploy Hyperledger in your environment and not have any other nodes that are outside your organization? Absolutely. But again, the blockchain software and services was really developed by a group of consortium members. Private blockchains have benefits. Now, let's just cover some of the benefits. Enterprise permission, that's the main thing. From a security standpoint, you control access. However, because it's private, you have less nodes, less scalability in the sense of the number of nodes. Now, you also have geographic, basically, locality in most cases. So for example, you can get faster transactions by reducing the number of nodes. And that's one of the benefits of an enterprise blockchain, because you don't have nodes that are, spread throughout the world. They're localized. Better scalability. You could scale them locally in the sense, once again, we know that once we start putting our blockchain in a more geographic fashion, that is going to slow down the transaction response. We'll support compliance. Again, this is one of the big deals around blockchains for enterprise, is to support compliance requirements. Consensus could be more efficient, and a lot of that is because you have less nodes in the blockchain. Now, when we compare features, again, we want to look at public and private. One is open read and write to the ledger. The other is permissioned. Identity is anonymous and public, whereas in private, it's known identities. Security and trust is open versus controlled. And again, we know essentially that the consensus will be different. And also, is it open source or not? Some good examples is comparing Ethereum and multi-chain to Corda or Quorum or Hyperledger. And here's a comparison between public and private blockchains, the most common, the top 5 essentially. And when we consider permissioned or permissionless, some things you want to take into account could be everything from governance to the industry vertical that you're in, to smart contract functionality, cryptocurrency requirements, consensus, costing, integration as well. Let's move on. Let's talk about trust and how trust is really an important factor in blockchains, and also how this can really affect security and your security posture as well. One of the areas around blockchain is that trust needs to be established, and this is usually done via transferring trust from typically an intermediary to software code. Generally, when you're storing data in the blockchain, it's going to be stored through cryptography as well. This is done as a private and public key pair. When it comes to trust in the blockchain, basically, you're essentially having faith that the transactions that are occurring on the blockchain are trustworthy. The users of the blockchain basically have confidence that the transactions are real. They're not fake. They're not going to be defrauded, that the data has not been modified. When it comes to trust, we want to understand that blockchain technology is really about storing data, and that data is usually in the form of a transaction. And when we talk about Bitcoin, for example, we want to understand that trust in Bitcoin is a direct result of the users trusting the code and trusting the encryption. And again, it's all part of having that holistic trust in the platform and also the players as well. This is a form to transfer trust. And again, we need to realize that that is part of the requirement. Now, when it comes to having types of blockchains and having trust in a type of blockchain, we want to realize, is it going to be a private blockchain? Is it consortium-based, or is it hybrid? And of course, if it's public, then we know that there's, no real management of essentially membership. When it comes to trust, one of the things we want to look at from a business to business perspective is that it could be time consuming. It could be repetitive.
There's typically a heavy dependence on paper or people. And if you have an intermediary, again, there's fees and charges that could be involved. When it comes to use cases, again, it's all about the implementation of the blockchain. If you can implement a use case for blockchain, the goal is to reduce the dependence on people, paper, manual processes, and reduce cost. Now, some industries really take to blockchain more than others. For example, the financial sector is a clear beneficiary of this. Payments between banks and corporations. Ripple's a good example of a consortium-based blockchain that they're able to make interstate trade with from a financial perspective, basically transferring value between banks and central banks for that matter. The consortium essentially has established trust. Now, when we talk about trustless, this is another term that's used. This is a model where you don't need to establish trust because you essentially have transferred the trust to the blockchain and you've removed the intermediary that you had trusted before. Blockchain is built on the premise of transparent code and essentially removes the need for intermediaries. Smart contracts can reduce the need for accountants, lawyers, bankers, and other intermediaries. When we talk about trustless, financial transparency can result through the use of blockchains and reduce those intermediaries. We know too that blockchain is based on a consensus algo. And if the nodes agree, then the transaction's valid. We can trust that the nodes in the blockchain will perform based on policies and based on the smart contracts that are set up. The blockchain and the ledger directly act as a trust broker. And this is the magic of the blockchain. This is where the software-driven world can really make efficiencies come to light. Let's go ahead and move on. Risk assessments. Let's talk about what a risk assessment is, some of the best practices around it, some of the considerations. Generally, risk assessments are multifaceted, holistic, and time-consuming. Basically, when I say multifaceted, what I mean is that there's many different aspects that you need to look at, such as the hardware, the software, but also different end user concerns, but also enterprise concerns or customer concerns. Holistic is really all-encompassing. How does it really fit into the enterprise? And then time-consuming is exactly what it sounds like. There's a lot of time that you're going to use manpower to determine what exactly the risks are and how to run these assessments and then mitigate after the assessments. So you want to have competent people working on these. Blockchain has benefits, advantages, and challenges for that matter. We need to address these and understand what these are because, again, as part of the assessment, we want to be able to take that multifaceted, holistic view basically to be able to get all-encompassing essentially. When it comes to considerations, we want to review our infrastructure, our membership, our CA essentially as well, smart contracts, compliance, and of course attend to any regulations. When it comes to risk mitigation concerns, we want to realize that, first of all, blockchains have been oversold. There's no question that blockchains were really built for specific purposes. They weren't really built for performance, for example. In other words, if you get a blockchain, under no circumstances should you expect it to perform like a centralized database. It's just the reality. It's not going to compete. Now, when it comes to risks, one of the things that we want to realize
is that we need to make sure, first of all, that the blockchain for a use case is actually a valid use case. Again, you can't expect to handle 10,000 transactions per second on any blockchain, no matter what the jargon says. And if they do say, even 1,600 transactions per second, that's still, not even realistic on a blockchain. Now, again, if you do get, like for the example of Hyperledger, they state approximately 3,500. Now, that's not a realistic config. That is more like the minimum number of nodes as close as possible with no real infrastructure. That's not realistic. That's not how enterprise deploy blockchains, nor even networks for that matter. Node distribution. You have to look at how your nodes are really distributed. We want to look at, for example, do we have these nodes distributed in the US? Are they in the US, in Canada, or are they in Europe or Singapore, wherever they may be, and look at any kind of risks that could come with that, especially around compliance and governance for that matter. When we consider risk assessments, these are critical before and after your implementation. We want to, of course, perform something beforehand and then after it's been implemented. We want to consider risk assessments as a next step after performing what's called a business impact analysis. A BIA is basically going to analyze your business functions and then look at any kind of loss that could be realized because of some impact to that function. Now, when it comes to identifying risks, we want to look at several areas such as data privacy, permissioning. We want to look at liability and any legal pros that might be involved. If you're using Corda, you may want to consider specific detailed actions around identifying legal pros and how that needs to be addressed on not only your side of the house, your enterprise, but also any customers as well. We need to look at compliance holistically, but also in a detailed manner. For example, are blockchain nodes, are they located in the US or are they not? And if we're dealing with European Union issues, we need to consider compliance issues around GDPR or other facets like know your customer as well. These are concerns that you have to dive into. And when we talk about management and monitoring, we want to have visibility into our ledger to manage what exactly is going on. Typically in a centralized enterprise architecture, generally, we have to manage our data. We have to manage the quality of the data. We also need to monitor who is doing what and where, identify vulnerabilities. There's a lot of things we have to consider. So, for example, when we consider visibility of a ledger, we generally want to make sure that the data that's on that ledger cannot be removed. We need to make sure that there's no way to remove any immutability of that ledger. We want to make sure as well that we can't just muck around with our algorithms, for example, or encrypted data can't be modified. But we also want to monitor the status of our blockchain nodes. And to do that, we need to, of course, set up monitoring. It could be done in many different ways, depending on the blockchain that we're looking at. Remember, too, that these are essentially servers, and we could monitor the servers from a virtual machine perspective as well, in most cases, or containers. Performance. Once again, we have to look at performance and determine how are things working. What is the transfer rate or the transactions per second? We need to also look at not only performance from like a transactional perspective, but also to identify performance around our regulatory requirements, for example. Look at enterprise integration. How does it all fit in to our enterprise? And also, too, how do we get back our nodes or our ledger information if there's some kind of recoverability concern? For example, is there a disaster that happened? Is there an availability issue on one of the nodes? What is the concerns we have to deal with? And to sum it all up, we want to be able to perform what's called a business impact analysis. We're basically doing this before we perform the risk assessment. We need to identify what the functions in our enterprise that could be at risk. We then go ahead and perform that risk assessment. We look at all the bells and whistles, all the features, all the hardware, the software, all the compliance requirements, our smart contracts, you name it. We try to determine where the risk could be. Once we've identified these risks and vulnerabilities, we then have to determine how to remediate these risks and vulnerabilities. Let's go ahead and move on to the next module. Let's talk about risk mitigation. When it comes to risks, generally when we get to the mitigation part, we've already identified these risks. So whether it's a 51% attack or a denial of service attack or any other kind of attack or vulnerability, we need to first consider a few things. When it comes to risk mitigation, we want to define it as taking steps to reduce adverse effects of that risk. Now, there's generally 4 ways to approach risk to reduce the risk adverse effects, and that could be through essentially what's called mitigation strategies. Now, when we look at a mitigation strategy, we know that there's 4, and this is really more related in a lot of cases in the old realm of IT around disaster recovery and business continuity, but it's very effective as well with blockchain. So let's talk about what it is. The first mitigation strategy is risk avoidance. In other words, the best way to not have a risk is to avoid it, right? It's fairly straightforward. When it comes to risk mitigation, that's when you're actually taking steps to reduce the chances of that risk happening. For example, if you have a firewall port open that shouldn't be open and you turn that port off, you've mitigated that risk of that port being open and exploited. Transfer risk is where you're going to look at the risk and find ways to get the risk out of your hands. A common way of risk transfer is generally through forms of insurance, for example. Risk acceptance is saying, okay, well, it could happen. So like if you buy a house in Iowa or over in Nebraska in Tornado Alley, you know that the risk of a tornado could be very great depending on the time of year. Again, fairly straightforward to understand the 4 mitigation strategies. We just now need to understand how we can apply it to our blockchain security. Now, one of the first concerns I always need to talk to customers and students about is company data. As a fairly well-known cloud architect and blockchain entrepreneur and basically all around consultant, one of the challenges I always run into is trying to understand why some companies are really good at understanding their data is actually an asset, whereas other companies may not actually consider their data an asset. And I know, in most cases that's probably not true, but you would be surprised the number of companies that don't take any steps whatsoever to protect their data. With that said, if you have data as an enterprise, that should be considered as an asset. And what do you do with an asset? You typically protect it. Blockchain distributed ledgers are immutable. Now, we also want to make sure that we understand that in that because of the fact that it's an immutable ledger, we need to protect that immutable ledger. What do we want to do? We want to back it up. We want to have copies of it. Now, in the world of Hyperledger Corda, and when we compare against Ethereum, things are done very differently. We're going to have to appreciate how data is maintained. For example,
If we're looking at Corda, we have essentially the practice of having a vault and local storage. However, in Hyperledger, things are done a little differently. And then if we look at Ethereum, once again, things are done differently. We need to realize how our immutable data is being kept. When it comes to data, it may or may not be distributed. Well, what does that mean? Well, once again, it really depends on how your company is maintaining their posture around not only data protection, business continuity, but also compliance as well as governance. Because, for example, you may have a US-based application, but it may actually have users from the European Union or from Singapore or Canada, let's say. Each of those countries have different regulations on how to approach data for their citizens. You need to be aware of that. There's a whole, course just in compliance and how to deal with that. Now, blockchains have restricted access, but that does not mean that everyone should have access to the ledger. A lot of blockchains do solve this problem and implement a privacy approach for transactions, even on a blockchain that has members that are authorized to be there. For example, in Hyperledger, we could implement what's called a channel. This may solve some of the privacy issues that you may have. Corda has a really interesting approach in where their blockchain network is really more of a point-to-point or peer-to-peer approach. It's a mesh approach where every peer basically can have, or node I should say, basically will communicate directly with the recipient, and it's not transmitted to all the other nodes, for example. Once again, every blockchain has a little different approach. We're going to focus, again, on each of these in the different sections that attend to the blockchain more deeply. But for this, we want to make sure that we understand the high-level techniques. When it comes to additional risks, some of the things we want to think about is certainly around compliance. We need to really pay attention to that because of the fact if they don't meet compliance, we may not exactly have a security vulnerability, but we may be exposing our enterprise to additional fines or regulatory oversight that we may not want. Data confidentiality. Okay, now this is where there's a lot of concern around how data is handled, how data has been shared, how data is protected. And to be very honest, you could just look at, for example, the Equifax hack that had happened back about a year ago or a year and a half ago, where they had known vulnerabilities in their Apache services, essentially, and somehow never got around to making those updates, even though they were personally notified several times by Apache to take care of this. Once again, this is all about, in a lot of cases, probably not technical in the sense of Equifax, but more of a culture of we'll just deal with it whenever the heck we feel like it. And as a result, lots of folks, hundreds of millions of people, were literally exposed from the paperwork that's been online. With that said, what I'm trying to get at here is make sure that data confidentiality is a concern. For example, some blockchains, such as a Hyperledger, are centrally administered. While others may be centrally administered, not all actually would be transparent to all the consortium members. For example, in the case of Corda. We do know that blockchains are essentially newer technology combinations. Basically, you have older tech melded together, and therefore lies a significant knowledge gap in numerous enterprises. We need to address those knowledge gaps. When it comes to concerns, again, we sort of talked about the concern that blockchains have been oversold. The fact that, again, they're really meant for privacy and confidentiality, in a lot of cases. But again, if you have an enterprise where the blockchain wasn't really sold or designed properly, there could be some challenges there. Once again, mainly around compliance, but I would also, suggest too that if you don't have the right solution, other risks could come up, such as user experience issues or not meeting the requirements of the enterprise. Now, let's talk about protecting your enterprise data. Now, one of the areas that I generally run into in most organizations, and not just in the blockchain world, in cloud computing, for example, as well, and data management, is that sometimes companies don't even have any kind of governance policies in place. This could also be known in some organizations as a security policy. It is fair to assume that if you don't have instructions or detailed routines and policies, etc., on how to handle data, then you shouldn't expect your own employees to be able to do that as well, or your customers. With that said, you need to have this policy at least attended to. Now, what about thinking of data from not only an output after we have it, but what about the inputs? How do we validate the data? How do we know it's actually going to be good data? For example, one of the risks could be an API input issue, or could be other issues around the ingestion points for data. Once again, we need to look at, is the data valid or not? We need to implement some specific routines. For example, in the case of Hyperledger, Hyperledger uses a little bit different approach than a lot of other blockchains. For example, it follows what's called an execute order and validate workflow, or control flow actually. And what it does is to help facilitate the transaction processing. It actually orders the transactions before it actually validates the transactions. And basically validate in the sense that it needs to make sure it's part of the endorsement policy that each of the transactions have the required number of endorsements, has the required certifications, for example, around certificates, has the right policy set as far as an endorsement. Again, we need to make sure that that's part of that. But also, too, if we look at implementing other security measures when it comes to not just Hyperledger, but other blockchains, we want to make sure, for example, in our API connections, that we have the right external connections, but also that all the components attached to our API connection are actually secure, that there is a perimeter, that everything is set up properly. We should also note that the APIs out there could be misconfigured, it could be compromised. We need to pay attention around where we get our APIs or SDK kits, etc. A lot more to that from a development perspective, but I think it's critical to discuss that. Let's go ahead and talk about restricting access. Now, when it comes to restricting access, we of course don't just want anyone in our enterprise. We need to have membership set up. That could be through an MSP. That could be through third-party authentication. It could be through directory services, whatever the right approach is for our enterprise blockchain. Generally, you're going to want to use some kind of MSP. An MSP is what? A membership service provider. We also need to look at not only that MSP from allowing folks in, but they could actually be vulnerable by a DDoS attack as well. Because again, if someone can get the IP address for that MSP, then it is possible to bring it down. And also meet compliance requirements. Again, this is the million-dollar question, is trying to identify the right compliance and address those compliance requirements efficiently. We need to also remediate network vulnerabilities. And this is one of the more challenging areas, I think, because a lot of good blockchain engineers are really good at data, big data, databases, but they don't have a lot of network expertise. And this is where you need to engage the right people. With that said, let's move on and talk about some other areas of blockchain security. Let's discuss some benefits of compliance. Now, when it comes to benefits of compliance, we're really talking about benefits that the blockchain can bring to your organization around compliance. Basically, we would have a tamper-proof record of immutable, fully auditable data. It could also be transparent to users and also for monitoring tools as well. We could also monitor reliability of services and the quality of the data as well. Now, when it comes to essentially the main benefits, we can look at it as smart contracts essentially are working on this blockchain platform, and the rules that we encode in these smart contracts can be enforced, but we can also audit these rules and smart contracts as well. It also provides a unique source of truth with consensus. In other words, it's not just one node saying that that the data is correct. It could be numerous nodes on the blockchain as well. For example, in Corda, we may have what's called a notary. And again, these are just things to think about on how the blockchain that you're looking at may actually provide this benefit. Now, blockchain technologies can also reduce risk around settlement, counterparties, and then also prevent fraud as well. Let's go ahead and move on to the next module. Let's talk about compliance requirements now that we know some of the benefits of being compliant. When it comes to blockchain, the first thing we want to realize is that it does present new challenges to your organization, but it can also provide opportunities as well. Now, when it comes to permission blockchains, generally these are going to enable compliance much more easier because of the fact permissioning controls who accesses what, the membership. Also, too, you can maintain the nodes where they need to be. You don't want to have uncompliant nodes and uncompliant geolocations. Another thing that we want to think about is how permissionless blockchains play into this. In reality, permissionless blockchains do not attend to compliance well because of the distribution of our nodes, but also to the lack of permissioning for our membership. Now, we need to also look at how data is controlled, how our organization stores their data, what's publicly available, what is not. One of the things to point out too with compliance is sometimes compliance can be really great when in the blockchain, but it can also be a challenge depending on the compliance requirement. For example, one of the areas the blockchain does pretty poorly in is attend to compliance requirements that have a portion or pretty much the whole regulation around the right to be forgotten. Basically, if you're in some countries, one of these I think is actually Canada, you can't actually keep data forever, and therefore if your customer calls up and says remove me from your database, they have to be removed from the database, and you have to provide compliance confirmation that they've been removed. So how do you remove someone from a blockchain when it's immutable? These are really big challenges to think about, but in reality, blockchain is not the right use case for that type of compliance. Blockchains may induce efficiencies for compliance, for example, around audits. If you have a blockchain and it's properly managed, it can actually enhance the audit experience. When it comes to requirements as well, we want to make sure that we understand that the blockchain will play a critical role in several ways for compliance. The first is to enable enterprises to operate lawfully in a dynamic and changing regulatory environment. Essentially, we want to make sure that the organization meets the requirements of the compliance and regulations provided in that it can scale to meet those needs. Blockchains certainly have the potential to change the way investigations and audits are completed as well. We also want to understand that they can provide transparency that can be implemented as well through like a blockchain explorer. Now, when it comes to additional requirements, we also want to understand that the blockchain will, of course, play a critical role, but we need to keep in mind, are we talking about permissioned or permissionless? Or is it a hybrid blockchain? Blockchains can enable compliance through permissioning and node distribution. Permissionless blockchains are open and thus membership is not controlled. Permissionless blockchains are geographically distributed as well. Ethereum had over 1,600 nodes at the time of writing this course and over 100 countries represented. Therefore, trying to maintain GDPR or PCI or anything is next to impossible on the Ethereum blockchain. Now, when it comes to compliance requirements as well, there's certain specializations that we need to consider. We need to consider PCI, for example. Now, when we consider compliance specializations such as PCI, HIPAA, SOX, GDPR, and FedRAMP, they all have varied approaches to how data is handled, how rules can be dealt with, how there's prerequisites, for example, how KYC is handled. Now, KYC is know your customer. With that said, what about if you're trying to do interbank commerce? How does the KYC, how is that handled by Bank 1, and does Bank 2 actually handle that appropriately? One of the challenges, especially with doing interstate or international transfers, is that there's a lot of customs and a lot of what I would call governmental oversight, not just in the US, but other countries. So a lot of it has to do with how you can leverage blockchain compliance, but also the compliance requirements, and how do you actually deal with, being in the same jurisdiction or not being in the same jurisdiction. Once again, it's one thing to transfer funds from one bank in the US to another. It's another to transfer funds from one bank in the US to one in Europe, let's say. So there's a significant amount of responsibility just in any of these compliance requirements. When it comes to some challenges, one of the areas is around smart contracts and legal pros. Now, we know that we could embed rules essentially into smart contracts. We know, for example, that we could meet compliance requirements as well by not only embedding rules into smart contracts, but also addressing the location of our nodes, the location of our network access points, the location of our users, and also the customers and partners that we deal with. For example, it's certainly one thing to have a use case for blockchain, but it's another thing to actually implement it. And my thought is we have to look at how the ledger is distributed. We have to look at the frameworks that are already there. There's a lot of contract law and international law to deal with. There's also, again, I mentioned the right to be forgotten and know your customer requirements. These are very detailed and very nuisance-oriented compliance requirements for a lot of organizations. We need to understand the requirements for identity validation. This is part of the KYC. We then also need to consider the centralization and distribution of blockchain assets, resources. We then need to identify, is the asset, is it financial or is it not? Now, when it comes to financial assets or non-financial assets, it could be, again, a money transfer, or it could be transfer of land. It could also be just something simple like transferring records from point A to point B. Anyways, however the blockchain is designed in your enterprise, you want to just validate how the compliance requirements will come together. Let's go ahead and move on.
Known vulnerabilities. Let's go ahead and discuss some common blockchain vulnerabilities. Now, when it comes to vulnerabilities, they're going to have a wide range of focus to be concerned with, but also a wide range of differences between platforms as well. So we could be looking at anything from endpoint vulnerabilities, API vulnerabilities, public and private key sets, key management, smart contract coding, having lack of standards, not following best practices. And then also, too, if you have a permissionless blockchain and you're using Ethereum or any other permissionless blockchain, they could be subjected to mining issues as well. Phishing could be a concern, and social media could also expose your organization as well. There's been a few attacks that have been able to utilize, for example, your laptop or computer when you click on a link or download software, for example, from the Apple Store, and you don't even know that you're running Monero locally. With that said, those are just some of the things to be concerned with. Now, one of the more common ones when we talk about permissionless blockchains is a 51% attack. This is more of a attack that is basically implemented typically by a malicious mining organization or miner. Could be a group or it could be just one person. And this essentially is going to use the compute power and will try to inject fake transactions. And this will cause, of course, some issues to process transactions that are actually good, valid transactions. When it comes to phishing attacks are very common. It's sort of similar to a domain name, and you go to that domain name and you think it's actually, for example, My Ether Wallet, and you don't realize that instead of myetherwallet.com, you go to a different one. Or, for example, malicious site might be .com, whereas a lot of the blockchain focused websites and projects are going to have, for example, a .net or .org in a lot of cases. Once again, there's certainly a lot of things to consider. You'll definitely want to replicate your wallets if you can. Maintain your wallet address and your keys. Try to pay attention to what you're clicking on. Again, ads will pop up on the internet, or when you go to the internet, it could be social media, generally Facebook or Twitter, etc. And you certainly don't want to have anything intercepted. And there's more info on this page here. It does a great job on going through how these phishing attacks actually work. When it comes to other vulnerabilities, there's a really great blog post here on medium.com. Some good graphics that go through different types of attacks that can happen and the consensus areas that you'll want to focus on. Now, this covers mainly permissionless. So permission are going to be a little different. We're going to talk mainly about those during this course is what we're going to focus on. So for example,
at the modules near the end that cover essentially Hyperledger and Corda, we're going to focus on. And also, when it comes to permissionless, we just want to be aware that there's a lot more to this. There's different types of attacks against Bitcoin. There was a Lisk attack as well. There's also attacks against Neo. Again, the goal of this course is not to get into all of those little types of attacks and vulnerabilities, just to give you that 101 level of things that can happen. So if you want to find out more about different issues that come up with the permissionless blockchains, go over to this link. You'll find out a lot more. Now, let's talk about smart contracts. This is generally where you're going to run into most of your issues, and this is why we want to focus on this right now. So the first type of vulnerability with smart contracts will be around access control. Essentially, you give permissions, and the permissions are not really advisable, and this is where the malicious user can gain control of your smart contract. Now, arithmetic is a vulnerability that typically is going to have, for example, a integer overflow in a lot of cases, but it could also be an integer underflow. And this is basically when you have a value that is not exactly ideal. And this can happen where the value may wrap around and essentially allows a large number to be a small number in some cases. Now, in this diagram here, basically the snapshot of the code actually, we want to just be aware that the integer here in the second line, if something happens and the amount is greater than the sender's balance, it can produce a negative result that can appear to be a large positive number and actually pass a check. Now, there's also a name for this in some cases, depending on the smart contract platform, but it could be considered, for example, PEC security, named it the batch overflow vulnerability. So definitely look into that if that's something you think you might run into. Now, return values. This is basically where you have an unchecked value. And this is really true, for example, in Ethereum. Now, in Ethereum, you can certainly have low-level functions that can return a false positive, for example, and throw an error. Once again, this can happen generally when a function makes a call and then somehow doesn't check the return value properly. And then what can happen is that low-level function can return a false result, for example, and can also be considered a false positive as a positive error when it may not be. When we talk about this one, re-entropy, this is sort of an interesting one because it's a term a lot of people may not totally understand. But basically, this is saying when the attacker, for example, tries to inject a vulnerability to your smart contract to try to change operations, what can happen is that the smart contract can withdraw functions and then send the value to another smart contract. And therefore, this is considered a re-entropy attack. Basically, you need to look at, for example, your fallback functions. You need to consider your smart contract approach to handling, for example, account balances. Is it possible that you could have a double spending issue? Absolutely. Now, denial of service is very common. We all probably have heard of that. But basically, denial of service is going to be when an attacker is basically throwing out a bunch of packets to your nodes, and it's shutting down your smart contract platform. Now, this can also be, for example, where there's so many packets that the vulnerability is actually not really anything that could be lost or stolen because of the smart contract. What'll happen is it just renders essentially that smart contract basically unfunctional or non-functional, I should say. Anyways, there's certainly a lot more, but one of the things to point out too that is really interesting is that Ethereum has sort of thought of this, and what they did is they built in a maximum gas limit. So when you're basically getting ready to propose a transaction, that gas limit will again limit what can happen. So if you say here is the max gas limit, it will not go over that amount. Now, bad randomness. This is actually another interesting one because what'll happen is a malicious miner can possibly manipulate some of the options in a smart contract and basically embed a secret code. Now, race condition or a race vulnerability is when you generally have two contracts, and the two contracts are essentially competing against each other. What can happen is if you are exposed to this race condition, an attacker can literally watch the transaction pool and then try to submit the same solution with the higher fee to win the rewards for mining, for example. But anyways, a malicious miner could, theoretically allow themselves to win the race and maintain the transaction fees. This one here is a little bit more complex, but look into it if that's something that you have not heard of. Now, a short address. Now, this one here is an interesting one because what is going on here is that essentially you have a short address. And if you look over here, you could see that we have line 2 and you have a bool, which is essentially a Boolean. And what can happen is that an attacker can basically exploit facts to an argument, which is essentially an argument to a function. And these are going to be stored essentially contiguously in memory. And therefore, for example, in Ethereum, automatically will pad the arguments to the correct length. Now, one of the things as well that can happen is if the attacker calls a function with the arguments, for example, where you have an address and you have an amount, for example, then, and if you see up here, it says address and then you down here amount, what can happen? And for example, Sencoin, this is really the main concern, is that the Sencoin function could be vulnerable to a short address attack. For example, because Sencoin does not impose size on its variables, the short address and also any amounts that are read could be passed again to, for example, to line 3. And when that happens, a transfer function could also be called, and essentially the attacker could essentially receive so many times the amount of ether, which again would not be welcomed. And in this case here, it would be 256 times the amount of ether that was actually, in this case, approved. So anyways, this is one of those vulnerabilities that takes a little work to really figure out, but just be aware of it. And then we have timestamp dependence. This is basically, in a nutshell, where you have a smart contract and the timing information that it is receiving could be actually blocked or actually vulnerable, for example, as well to attacks. And if the timestamp is incorrect, it could theoretically as well change the window where this smart contract may or may not work. So this is, again, a lot more to smart contracts and vulnerabilities and remediating them. It's a whole lesson and class in itself. I would advise you, if this is of interest to you, to take more of a development course that goes through a lot of this step by step. Let's proceed on. Hyperledger. Let's discuss some areas around Hyperledger that is really focused on security. We know that Hyperledger is really a smart contract platform that was really built by IBM, but is now maintained by the Linux Foundation. It was really designed to be a platform for businesses. And we also know that it's a cross-platform blockchain. And again, if you're using Fabric or Sawtooth, you have a lot of flexibility in how you implement your services. We know that Hyperledger Fabric is essentially permissioned. We also can appreciate that it has some properties. Identity management uses X509 certificates. Network privacy is private. We know that we could use channels in Hyperledger. We also know that the consensus is essentially pluggable. We also know that there's at least 2 available, depending on the version, of course, of Hyperledger Fabric, forms of consensus. And there's also support planned for a full Byzantine fault tolerant solution. We know that Hyperledger uses channels, and it uses these channels pretty effectively. We also know that with Hyperledger that we can go ahead and essentially use 2 different approaches for our blockchain ledger. Now, we know that with our world state, our database, we can basically select 2 databases. We have a choice of LevelDB or CouchDB. Now, we also know that there's a transaction log. We know that this is going to record all the transactions on the blockchain. Now, one of the things to point out around channels, for example, we had discussed in the channel section, is essentially that each channel in Hyperledger is essentially a separate blockchain. It's essentially a sandbox in the main blockchain for that enterprise. So for example, if you have 12 nodes on your Hyperledger Fabric network, you're only going to have 2 nodes that are going to essentially have visibility into that ledger on that channel. Once again, that's a really slick approach that they use to provide privacy. The chain code with Hyperledger Fabric, and as a refresher, we should know that in Hyperledger Fabric, chain code is a smart contract. We also know that it can be programmed in Node.js or Go. We're going to run this in containers as well. Now, Hyperledger is going to be a little different when it comes to transaction validation. Typically, most of the major blockchains, they typically execute, validate, and then order their transactions. Hyperledger does it differently. It executes, orders, and then validates. And it's done because of the fact that it's going to provide a performance boost in the sense that the transactions will be slightly quicker to be written to the blockchain and be processed. We also know that Hyperledger as well has some other benefits with the control flow, like parallelization, specialization as well. So for example, in the control flow for Hyperledger, we know that there's benefits, and the 2 major benefits is parallelization and specialization. In the execute phase, transactions can be validated in parallel instead of sequentially. Well, what benefit does that have? Well, it processes quicker. Specialization is going to validate in order, and these are distinct phases. This allows your nodes to specialize in one role or another. Basically, we know that Hyperledger as well has security measures involved, especially around like identity management, the architecture as well. Now, when it comes to execute, order, and validate, we pretty much already had talked about this in the earlier modules, but just realize that Hyperledger does have some benefits around transaction workflows. Now, what about security measures? What are we going to do to really lock down our Hyperledger Fabric blockchain? Well, generally, we want to use a pluggable identity management. It supports different schemes like LDAP or OpenID. We also should be aware that the channels provide some security features, but also privacy as well. Now, we know that the data is private, and in Hyperledger, it uses a gossip protocol. Now, this is actually very different than a lot of other blockchains where you have a transaction that might be propagated through the blockchain and every node gets a copy of that, updates its ledger with that transaction. Well, in Hyperledger, that does not happen because the gossip protocol will only go to the nodes that need to know what is going on. In other words, they're part of that transaction. If they're not, then that activity does not get propagated to the other nodes. With Hyperledger, it's essentially, of course, its own specialization. And we also know with Hyperledger Fabric that depending on our implementation that we deploy, how many nodes, how we're going to scale it, the type of database that we use for a world state. We also have choices around our consensus. We can definitely take into account a lot of moving parts, but generally we want to look at least 3 different areas with Hyperledger to improve our posture. So definitely take a look at your overall Hyperledger security, take a look at your distributed ledger, discuss around your developers, perhaps your smart contracts that you're deploying, and then consider other security features that are part of Hyperledger, like the identity management support. You get integrated with LDAP, OpenID. Again, a lot of good benefits there. Well, let's go ahead and move on to the next module. Well, let's talk about Ethereum blockchain security. Well, we know that Ethereum is a public, non-permissioned blockchain. We also know that it's open to the public. We know that it's using proof of work. And at some point, when it gets to the right block number, it will change over to a proof of stake consensus. Now, Ethereum was originally designed to be a smart contract platform. And again, it's perhaps the most well-used smart contract platform out there. With that said, we want to be aware that with smart contracts, for example, these are written in Solidity. And we also want to be aware that there's a ledger as well. Now, with the Ethereum ledger, it's really a little different than perhaps what you would see in Hyperledger, for example. It uses essentially a set of trees. And with this set of trees, you could think of trees as being branches. And these branches have different sort of shoots off of them. So we have a state tree, a storage tree, transaction tree, and a receipt tree. I won't go into each of these. This is, of course, a subject that you may or may not be too concerned with if you're not a developer. But basically, the main thing to get here is that the way the blocks are on the Ethereum blockchain, they're going to contain essentially hashes. And these hashes should have, of course, the roots of the current version of the trees, in this case, for example, the state tree, and we'll also have the transactions as well as the other relatively relevant information, such as the receipt tree, for example. And then we have, of course, our Ethereum virtual machine. The Ethereum virtual machine is going to run the smart contracts on the platform. Basically, contracts are going to be written in Solidity. And then each instruction in the EVM is going to have to be tied to what's called a gas value. Now, the gas value, as you may know, is going to be essentially an estimate of compute power required to process the transactions in that smart contract. Again, we know that Ethereum smart contracts run on the virtual machine. And we also know that if we want to execute a smart contract, we have to include gas. And gas is essentially going to be a fraction of the ether in most cases. And this pays for that computer essentially effort that is required to run the code on the EVM. Now, one thing to point out too, if you don't have enough gas, you're not going to be able to execute the EVM smart contracts. Now let's talk about security controls that can be at least appreciated in Ethereum. There's really very little you can do to improve security, to be honest. However, let's talk about what we can do. With Ethereum, we know that support for privacy and security is just about non-existent. In other words, when you make that transaction on Ethereum, it's open for the world to see. Now, we also know that security features are not directly supported by the Ethereum blockchain. You have to generally write them into your smart contract. However, this is going to change eventually. It is planned to support what's called zero-knowledge proofs. One of those is called ZK snarks, for example, very similar to some other implementations out there, such as Zcash. Let's go ahead and move on to the next module. Let's talk about R3 Corda. Now, R3 Corda is, of course, perhaps one of the more sophisticated blockchains out there. And because of the fact that Corda was designed specifically for the financial sector, essentially the main vertical that the consortium members were a part of, basically Corda was really built specifically for banking. It's not a cross-industry platform, even though sometimes you may see it, sort of sold like that. It really does not support cross-industry very well. Now, Corda was developed in 2016. It was meant to record, manage, and automate financial agreements. Now, anytime you hear financial, you likely should expect really robust security features as part of that application or platform. It was developed for the banks. Now, Corda, again, was really designed for business use cases that are really more of a targeted use case. Now, Corda also, again, as you may be aware, Corda blockchains have notaries. These notaries essentially sign a transaction for that to be valid. Basically, whenever you have a state, essentially, again, the state of the blockchain, every node has a copy of the distributed ledger and has an assigned notary. This notary will only approve transactions when it is assigned specifically as the assigned notary for the input states. Essentially, it has the following properties as part of this. It is private, it's permissioned. Identity management is the X509 certs as you would expect. It does have a pluggable consensus architecture. So Corda has, of course, a distributed ledger. And this is different than most blockchains. And the main way it's really different is because of the fact that every node on the blockchain does not have visibility into what everyone else is doing. And this is what really makes it unique. Access is on a need to know. I like to call Corda sort of similar to what we would call in the government sector compartmentalization, where only members who had a clearance would only know specific areas of their job duties and nothing more. So it's very compartmentalized, the access. Each node on the blockchain keeps its own copy of the current state and has a point of view. Corda uses point of view as the reference of essentially a world state. In Hyperledger, we call it a world state. In Corda, we would call it a point of view. States are consumed and produced by transactions, and each node keeps a complete history of both the current and the historical versions of all its states. When it comes to security measures, we know that it's a need-to-know philosophy. It uses notaries. We should also be aware that users can only see what they are allowed to interact with. Again, it's a need to know. It's compartmentalized. Corda uses TLS encrypted communications, and it doesn't use a peer-to-peer broadcast. In other words, it doesn't transmit any of the communications to everyone else on the blockchain. It only transmits it to the participants that need to know. Nothing more and nothing less. So if it's not a participant in the transaction, then the nodes won't have visibility into it. Again, a pretty ingenious approach to a blockchain, in my opinion. When it comes to Corda, we know they're dependent on notaries. We also know that with Corda, the notary is essentially similar to a truth agent. It basically will allow or not allow, and it's going to permit a transaction to happen if it is authorized to happen. When you're implementing a Corda blockchain, notary trust and security is paramount. Let's go ahead and move on. Now, I'm over here at the anders.com blockchain hash demo page. This is a really cool website. They've got an SHA-256 hash demo page. They have a block and a blockchain and some other pages as well to look at. Now, let's just briefly talk about what we're going to do here and why it's important in regards to blockchain and encryption. Now, generally, a hash algorithm, what it's going to do is take that data that I'm going to enter and put it basically into what's called a fixed length hash. Now, what should happen is every time I enter the same data, I should result in getting the same data out. Now, when I modify the data by, let's say, one number or one letter, that'll totally change the hash. But basically, whether it's Bitcoin or Ethereum, in general, hashing works pretty much the same. But for example, in Bitcoin, it uses an SHA-256 hashing algorithm, and it uses what's essentially random numbers that will generally allow the Ethereum protocol to use what's called a predictable amount of CPU effort. And that's why, for example, with like Ethereum or even Bitcoin, they're able to estimate the cost of processing that transaction because of the fact the hashes, the signatures are steady. When you generate that hash, basically this will, of course, provide a result that should be expected. So let's go ahead and give it a try. I'm going to go hello Udemy. Okay. Now, if you look at the hash, you can see that it's 903 and then it ends in 1219. Now, let me just change that by one digit. Let me go Udemy. Now, you can see that that totally changed. Let's go ahead and put back the Y. And again, what do we have? That same exact hash ID. And when I add blockchain there, let's say, you can see that the hash begins with a BA and ends in a 5E. Let's go ahead and take out an N. And you can see that that totally changes. And I take out another one that totally changes that hash. Let's go ahead and put in the IN. Now you can see it goes back to the BA and it goes to 5E again at the end. So just think of it from this perspective. The hashing algorithm was what essentially is going to take that input data and turn it into a fixed length hash. Because of the fact that hash will result in the same data, basically it won't change the output if it's the same data. However, if you change the input by one, then what happens? The output will be totally different. But basically, just like any compute data, for example, these are going to be large numbers, and typically too, it's going to be written in down here. You can see it's hexadecimal. So with that said, just be aware of how SHA 256 works, and just have a good understanding. It's fairly simplistic. Now let's go over here to block. Now you could see when I go to block, I have a hash already there. There's a block ID of 1. If I take out that block ID and I add in let's say 33, you can see that it starts with 7-1 and it has an F3. And then let's go ahead and change it to 31. And you can see that it ends in 6-7. And then I change it back to 33. To see that there's F3 again. Now, let's enter some data. And you can see that when I go hello world, it ends in 9-4. And then I take out the D. As expected, it changes back. And now what I could do is if I go here to mine, what's going to happen is it's going to go ahead and essentially what this is doing is representing essentially writing to the blockchain. And so what's going to happen is it's going to take the previous hash, basically, and make sure it's aware of that. And you can see that the block ID is 33, and the nonce that was chosen. Remember, the nonce is a random number that's chosen. And again, you can see that that's how that changes. Now, what about if I change the nonce? You can see that the hash changes as well. I change it back to 5. Guess what? I get the same hash. Now, let's go over to blockchain. Now you can see this actually happen in sort of a workflow. Now I have block 1, block 2, and block 3. You can see the nonces are totally different, and there's no data. What I want to do is I want to go hello Udemy, and you can see that my hash is D7 and it ends in AB. Now you can see that the previous hash, what's it represent? D7 ends in AB. What's this hash here? So basically it's referencing the previous hash. And then this one here, what's it doing? This hash here is being referenced by the third block. And if I go hello Udemy, what happens? Basically the hash changes again. And again, block ID, different nonce. So this is a really cool tool to play around with, just to give yourself an idea. And again, if you go down the line, you'll see that it's going to reference the previous hashes. So this is called anders.com blockchain/blockchain.html. The link is in resources. Give it a try just so you have a good idea of how things work.
In this solution, let's discuss adding a member to the IBM blockchain as a service. Before we get started, I just wanted to point out where you can go to find out information about credits that you can receive to use the blockchain platform as a service with IBM. Now, if you go down to this webpage here, it's ibm.com/blockchain/platform. They currently are offering a $500 in credits when you join the starter plan. Now, once again, this may not be the right choice depending on where you're located geographically. I'll leave that up to you to decide. Now, the starter plan includes the ability to use it for 30 days in the default config, allows you to use the Hyperledger Fabric features, deploy apps, allows you to use free code samples, and also just learn the platform. That's what it's meant for. It is a developer platform. There's also an enterprise plan as well, and there's additional cost for that if that's something of interest. So you want to go select here to get started now. What you would do is fill out this information and just follow the instructions when you claim your credits. Let's proceed over to the website to log in. Now I'm at the login page, so I'm going to go ahead and log into the service. And this will bring me over to the dashboard. As you can see, it's still loading the dashboard, and the dashboard is empty because, of course, I deleted the services after I used them for development and training. Now, what we want to do now is we need to go and create a blockchain network. The first thing we want to do is go select Create Resource. We then want to go search for blockchain. That's really the fastest way to find it. You could also go over to databases as well and look over there. I'm going to go select blockchain. Now, one little word of wisdom when you use a service, that it's located in different geos. So it's Sydney, Frankfurt, London, and Dallas. Now, currently, at the time of writing the course, the starter plan is only available in Dallas. Now, if for some reason Dallas is not available, you can go to either Sydney or Frankfurt or London and spin up the enterprise plan. However, this is a course at the time of writing. Now, also, you may want to see if down the road, again, this is 11/27/2018, and just validate what's available at the time. For folks in the US, Dallas would be, of course, the best choice. However, if you're in Europe, you may want to look at Frankfurt or London, or in Asia, Sydney. The one thing I will say is IBM has consistently, in the last year, moved up and down some of the database services. So some of the services that were available, for example, in the South or in Toronto, are not available now. So please do check and just validate if Dallas is the best option at the time that you use this course. Let's go ahead and create a resource. Now, one of the things I'd recommend too is, again, this is the starter plan, tells you what's included. The enterprise plan is here. So let's go create. Now, what's going on right now in the background is that this is spinning up essentially a Cloud Foundry container with your blockchain network in a container that is essentially Cloud Foundry based. So the network has been created. So what we want to do is launch it. Now you'll see that it'll pop up a let's get started. It'll do that every time that you deploy a new network. So feel free to just use the let's get started, the demos and stuff. You could also turn it off here if you want as well. Now by default, the starter plan starts up three specific types of nodes. We have an orderer node, a CA node, and a peer. Now, the orderer node is responsible essentially for managing how the transactions are processed on the blockchain. It's got several other duties, but that's just sort of the main role. And then we have the CA. That's a certificate authority. This is part of membership services. And then we have a peer. Now, effectively, what we really want to do in most cases is to add another peer down the road if we want to actually set up a policy where we need to have several peers validate that that this transaction is actually a good transaction as part of the process with Hyperledger. But what we want to do now is just walk through adding a member. So we want to go select member. You can see that I'm a member of two different companies. Now, also by default, it creates two organizations for you, which is Company A and Company B. What we want to do is go ahead and just leave it at Company A for right now, because we just want to just add a member, nothing more. I'm going to go ahead and add a member. I want to invite the member, so what I have to do is add an email. I'm going to add another one of my emails. I'm going to go ahead and add it as well. And again, it could be a name, it could be whatever you want. For the name, I'm just going to put in a note and add a member. Now you can see that it says pending, and that is a good sign. The next thing we want to do is this member who is being requested to join by the requester, which is my other email, will need to log into their email, and they will receive an email that will say join the network. So let's go ahead and validate that I received this email. So I received the email, I had the invitation, and then the next thing you know we'd want to do is select proceed. And when you do select proceed, it will bring you over to the blockchain website. You'll want to, of course, follow the instructions if you want to set up that additional account. Also note, if you wanted to log in with the API, it gives you your network ID and location ID for the API if that's what you like to do from an API perspective. Let's go ahead and proceed on to the next module. In this module here, we're going to go through the solution for Corda. Demo bench download. Let's proceed. We are at the Corda.net download.html page. As you see on the download, there's not just demo bench, but there's additional solutions you can download, such as the source code and the enterprise solution as well. Now, Corda Demo Bench is meant for you to install locally on your desktop, such as your Windows or Mac OS box. You have the ability to do that. It's very simple. It's free. Let's proceed and download Demo Bench. Let's select Demo Bench. It will bring us over to the Demo Bench page. It'll give us two choices, a Windows installer or a Mac OS. Let's select Windows. Now this will take a minute or two to download depending on the speed of your bandwidth. It's about 260 megabits. So this will come up in a few minutes, and I'll come back when it is done. The download of the executable has completed. Let's go ahead and install. I'm going to go ahead and select Run. This will walk me through the setup. I'm going to go ahead and select Install. This will take approximately a minute at the most, depending on the speed of your system.
And essentially we'll go back to this when it is done. The install is completed and it popped up the Corda demo bench application. Now when we first log in, it's going to go ahead and produce a new node. Basically what we want to do is go ahead and start the node. Now we could change the node to whatever we want. In a Corda config, we need to have at least a notary to validate transactions between the different nodes. Now, what we want to do is we'll leave the notary the way it is for the demo purposes. Now, there's two types of notaries. There's a validating and a non-validating notary. We're going to leave that the same. I'm going to go ahead and start the node. Now, what happens is this is going to boot up a small virtual machine instance running Java virtual machine. And this will go ahead and start up. As you see, it's starting the RPC connections, the peer-to-peer messaging, and it has completed. Now there is an interactive shell as well. For the demo here, we're just going to proceed and set up some transactions, but feel free to investigate that if that's of interest. What we want to do is now go ahead and add another node. I'm going to call this INE Raleigh, and I'm going to put in, since there's no Raleigh there is a Charlotte which is close by. We'll call it INE Raleigh office, which the nearest city would be Charleston, or Charlotte, North Carolina, that would be. Now what we want to do is just go ahead and select currencies that we want to be able to issue. I'm just going to go ahead and select the GBP and the US dollars, but you could also select whatever you so choose. I'm going to go ahead and start the node. And it is starting up. So we have that node up and running. Now what we want to do is add one more node. Feel free to call it whatever you want. In this case, I'm just going to call it Bank of New York City, and the nearest city would be New York. We're going to go ahead and issue GBP or US dollars. Going to head and start the node. And this will start up. And after it starts up, what we want to do is set up a transaction. Okay. Now, just clarify where we're at so that we are all on the same page. We have a notary. The notary is going to go ahead and validate that the transactions are valid. They're going to basically essentially notarize is the reason it's called a notary. We have INE in Raleigh and the Bank of New York City. Let's go ahead and launch the Explorer. Now the Explorer is up. Let's go ahead and focus in here. What we want to do now is we'd like to send a transaction between Bank of New York and the Bank of INE. Let's go ahead and just validate. We don't have any transactions right now, but we want to go to cache and we want to go ahead and select a new transaction. When we select a new transaction, we want to go ahead and issue from the Bank of New York to the Bank of INE. I'm going to put a reference number. Now, the reference number is basically just a number that you're going to assign. It could be 1, 2, or whatever number you're going to put in there to identify that specific issuing of the currency. I'm going to go ahead and select US dollars. Let's put an amount of $100,000. Now we're going to go ahead and select execute. Now pay attention to the messages when it starts. You could see that the cash was issued. Let's go OK. Let's go to transactions. And you could see that we had no transactions earlier. But what we do have now is that we had a transfer from the Bank of New York, issue $100,000 and move it to the INE Raleigh office. Let's go ahead and perform one more transaction. Let's go to the dashboard. Just validate here. You can see that there's 2 there. And we go to the treasury. You can see that there's nothing in there yet. We'll go ahead and take a look at that as well. But just validate here. We go to transactions. That's basically what we expect. Let's go to network. Now on the network, you should be able to see that there's 3 specific basically icons, little targets, I guess you would call it, that specify INE Raleigh, Bank of New York, and the notary in Rome. With that said, let's go back to transactions. Let's validate what we have. And we could also go up here and validate that we're on the right node. Let's go back to the dashboard. Let's go back to cache. And now what we could do now is basically go new transaction. Let's go ahead and issue from the Bank of New York to INE again if we want. Let's do 2 instead of 1. And I'm going to do, let's say, $1 million. Okay, that's $1 million. And then currency will be in GBP, which is British pounds. Let's go ahead and execute. And that has completed. Let's go to transactions. And you can see that it moved the funds. Now, what we want to do now is go back to the dashboard, validate that this has occurred. Bank of New York, let's exit Corda. Now let's go to INE Raleigh. And if you go here, you can see that there's transactions for balance of 0. INE Raleigh, it shows us the balance of a million GBP and 100,000 US. States in the vault. Let's go ahead and launch the Explorer. Now we could see there that when it comes to transactions, this is what has been recorded. Cash available here is basically listed here in US dollars and GBP. Let's go ahead and view our network again. And you can see the notary, and because of the little screen issue here, you can now see the Bank of New York and Raleigh. Okay, let's go over here now. And let's go to the treasury. We can see that we have our funds there as well. Okay, last thing we want to do is let's go to settings. Now, what we could do here is we could select, basically, when we go to edit, we could edit the reporting currency to be one out of the 4 currencies. We could select full screen, we could do remember me, or we could specify a specific host and port to utilize as well. In this case, we'll just go ahead and skip over that. We'll leave it at US dollars. And that's pretty much some simple little transactions that you could do on Corda Demo Bench. We could see that I'm on Raleigh at the point right now. Let's go ahead and exit out of Corda Explorer. And then if we go to Notary, we could launch Explorer as well. And let's go ahead and adjust the screen. You can see that the number of transactions that it was a party to it notarized was basically listed here. And again, go to cache. We could go over here as well to new transaction and select pay as the payer being notary. We could select the Bank of New York. And if there is funds available, we could go ahead and, of course, issue that as well. So in this case here, a lot of flexibility we could use. Now, because it's a notary, there's no need to have currency, but I just want to show you that if you did want to set that up that way, you could as well. With that said, it notarized 2 transactions, Bank of New York, issue, and issue. We could expand on that. It tells us information that it was £1 million, has a signature there as well. And if we scroll over here, we have the signature for this transaction, which was $100,000. The best way to learn this is just to play around with it, set up different transactions, and get to know the Corda demo bench. This is a great tool for utilizing as a proof of concept or a demo in a lot of cases as well. With that said, let's proceed on to the next module. In this solution, we're going to go ahead and walk you through what Metamask is, what it's useful for, how to download it, how to sign into Metamask, and discuss some areas around Metamask that I think are really, I guess, interesting, even to probably an architect or a sales engineer. We're not going to focus on development. Again, that's a whole different subject area, but we want to give you an idea of some of the tools out there so you could see how things are being applied and what your customers may be interested in, for example. Now, one of the areas that I think is really, really useful, especially with Ethereum, is you have what's called Metamask. Now, Metamask allows developers to basically communicate with web apps that are not blockchain apps, but also allows developers to run an Ethereum node without actually downloading that full Ethereum node. Now, if you go over here, you could see that the Fox, of course, moves around. That's pretty cool. This explains what it is. It's essentially a bridge. It allows you to go to different parts of the web with your browser to run that DApp in your browser without that full Ethereum node. It includes a vault. It includes, the ability to sign for those transactions. There's a nice little intro here I'd recommend you look at. And you go over here, you go get the Chrome extension. So you click there. And this would be the extension. I already have it installed. And you can see if I click here, there's MetaMask. Now, that's for Chrome. Now, if you don't want to use Chrome, they do have what's called the Brave browser. And you'd have to download the browser as well if you didn't want to use the Chrome extension. So that's really the only 2 options at this point. It is actually a very fast browser. So if you want to look at that, you could download that. But let's go ahead and look at MetaMask. Now, what I'm going to do is I'm going to go ahead and log in. I've already, created my account, and I also created what's called a seed phrase. Before I log in, let me show you. So you have this wallet seed phrase, and this could be anything that you enter, like, I went to Peru in August and I went salsa dancing. Whatever you want to put. Or you could put anything as simple or as complex as you want. And then you put in a password and you confirm it. So the passphrase and the password add that multi-factor capability. But you don't want to lose it, that's for sure. So you put in your password here. And that's assuming you put in the right password. And let me try it again. There it is. Okay. Now, I log in. You can see that this wallet I have called EtherJoe. Now, I have approximately, looks like $10 or so, $9.43. And Ether must have dropped since I sent it, just because I know it was over $10 and now it's down to $9. Anyways, very trivial amount, but just here to walk you through a demo. Now, this is, again, what's in the account. Now, I could go here, and I could go to Coinbase or Shapeshift, and basically it says, if I want to go to Shapeshift, basically the exchange rate here, you put in your Bitcoin address here, and you could transfer Bitcoin to get Ether. That's assuming you have Bitcoin. If you don't, if you're in the US, you go to Coinbase. I don't believe they're accepting accounts from out of the US. At one time they weren't, but they may now. So you may want to double check. So you go over here and you put in, whatever you want to put in, $12, $10, and you just put in your email and you just transfer it to Metamask. Now, in this case here, I already have funds there to play around with. Now, what you could do is go over here, and I select EtherJoe. I could go ahead and view the account on Etherscan. Now, Etherscan is the blockchain. This is basically showing you the transactions that this wallet performed. I have the ability, you can see that the Ether value is $9.45. There's one transaction. Now, what I'll do is I go ahead and send another transaction, and then we'll go back and check that. Now, if I go back here to Metamask, I could also go over here and put in a gas limit and a gas price of what I'm willing to pay for a transaction. Now, if I go up here, you can see that I'm on the main Ethereum network. Now, what about if I don't want to be on the Ethereum network and I want to be on a test network? Now, there's different test networks that serve different purposes. You also have the local host, and also you create a custom RPC. When it comes to the different test networks and custom RPCs, now, for example, let's go back to this menu here. And if I go down, like, for example, there's Ropsten and there's Coven and Rinkeby. Now, generally, you want to use the appropriate testnet for what you're trying to accomplish. For example, if you're doing early stage contract development, you may want to look at the Rinkeby or a local host. Ropsten is really focused for latter stage contract development. This is a very popular testnet. And again, you have the ability, for example, with Ropsten, to use the Ethereum network with free Ether, but it has poor security. So when you connect to Ropsten, just remember that the process is essentially using Geth, and it's simulates the Ethereum network and essentially allows you to test out that contract. Now, the reason you may want to use a lightweight versus a heavyweight testnet, so for example, Rinkeby, Coven, Ropsten, use Ropsten if you're really in that late stage dev. The problem with it is that it's slower generally, but the reliability could be good. So again, use the appropriate testnet. Your developers are going to be pretty good at figuring that out, but you want to have an idea to talk intelligently about maybe why you need to use one over the other, right? Now, if I go back here, I could go and send, and I put in the recipient address and the amount, and bingo. So I just sent another Ethereum request to my wallet here. Let's go ahead and take a look at the Ether scan and see if it has been received. I don't see it shown here, but sometimes there is a little bit of a delay. And as you can see, I sent $10 worth of Ethereum to my wallet address. So let's go ahead and check to see if it has been received in Etherstats. What we want to do is go over here and go over to the main area here. You can see nothing's been updated yet. That's okay. I could go over here, go to Etherscan, and you could see that 8 seconds ago there is a transaction that was pending. Now, this again, I've seen it take 10 minutes or so to update to Metamask. And let's go back here. And what we could do, let's just log out. Sometimes it's quicker just to log out than wait for it to happen. Okay. And you can see that it did update to $19. So it did update finally, and that's good. So that's simply how MetaMask works and how you could use it as a wallet, but also as a browser all at the same time.
In this module here, I just want to introduce you to some blockchain certifications that are out there, just to give you an idea around where you can take your career. And one of the steps to do that is to get certified in blockchain. Now, the CBSA is the Certified Blockchain Solutions Architect. This is by the Blockchain Training Alliance. It is a very valid and actually very common certification that has really taken off in the last year or so. It is an exam that you do need to go to a testing center. The cost is $300. However, there is a discount code that I have that I'll provide here shortly that'll save you 30% off. Now, the exam is 70 questions. It is performance based. To pass, you need a 70%. When you do pass, you will receive a package and it will include a certification token as well. To get the discount, go to the Blockchain Training Alliance site, go select under certification the exam that you want to take. This code is good on any exam, not just the CVSA. It could be Hyperledger or the Ethereum exam or security exam. So any exam, go ahead and enter the code. It will take $90 off. Now, for us developers out there, if you are a Corda developer, then you may want to get certified. Now, this exam is actually an online exam. You take it from your home or your office, and you pay the $150 to take it. But you take it open book, and you can have multiple attempts. The one thing I will say, though, there is a course on Udemy that you could take, the Corda Developer course. I believe they're offering the certification free as part of taking the course, which is somewhat cheaper than the developer certification exam itself. So you may want to try that. I can't make promises it's still available, but I thought that was something you may want to look at if you are a developer and would be interested in getting certified by Corda. Let's move on.
Well, we pretty much completed the course. Let's do a quick review before we close out officially. We covered quite a bit of material during the course. We talked about what a blockchain is. We know that it's a transformational technology. We know it's a decentralized database. We also learned that a blockchain is going to imply that transactions are going to allow you to update the ledger when you propose a transaction. That ledger can be accepted by others or not. And when that transaction is, it will update the ledger. Now, we know that blockchain is built from three technologies: peer-to-peer networks, private key encryption, and programs. We also learned that digital identity is critical to a permission blockchain. And we also know that we need to have private keys and public keys as well. We also learned that blockchain is disruptive to the status quo. We then learned that blockchains are ledgers that are shared among computers around the world. We then also discussed that blockchain has some security features, some security benefits. We also learned that blockchain is either permissionless or permissioned. That endorsement is really important in a private permission blockchain. We then learned about blockchain security in a permission blockchain. We want to ensure, because we have a permission blockchain, that we want to deny illicit attempts to change data that should not be happening. We want strict membership. We want to have identity management. We then discuss some of the best practices around blockchain security. We want to have code audits. We need DevOps processes. We want to perform due diligence. We want to have API and endpoint management. We want to have assessments by competent security professionals. We want to also train our users. And of course, we would want to integrate into our enterprise services. We then talked about Bitcoin mining and what mining is. We also are aware that there's best practices with blockchain security. We should have crypto wallets when we have permissionless blockchains. We need to ensure that they are safe. When it comes to software development life cycles, we know we could look at Agile, Waterfall, and various other programs. SDLC is meant to provide high quality software. We also understand that development and operations should equal DevOps, and that we know that DevOps uses agile software development. Blockchain and DevOps can certainly work together. When it comes to cryptography, we want to be aware that this is essentially the practice of securing private messages. We also learned that there's a workflow to our cryptography. We then discussed membership and why having membership services is really important in a permission blockchain. We learned that channels are going to provide a secure and private and confidential approach to transactions. For example, Hyperledger Fabric uses these. We then talked about identity and access management and some of the facets of what we need to be concerned with. We then discussed the differences between private and public blockchains. We then discussed the enterprise blockchains as well. We then moved on to understanding some of the considerations of permissioned and permissionless blockchains. We also learned that trust is epic in blockchain. We know that trust is a requirement. And as a blockchain user, we need to trust the code. We should also consider performing risk impacts, and we'd want to do this in a 3-step approach. The first is we need to understand what the impact is by performing a BIA, perform a risk assessment, and then identify the risks. And then the 4th step really is to remediate. Again, we want to take the steps, the 3 main steps, and then the 4th is going to do what? Remediate and fix the vulnerabilities. We want to then take our risk mitigation techniques that are listed here and again, make sure we apply the appropriate protections. And we also learned that blockchain brings new challenges, but also new opportunities. We want to ensure that we look at our blockchains to induce efficiencies. When it comes to compliance, one of the main benefits is to provide an ease to our audits. When it comes to vulnerabilities, we discussed various vulnerabilities such as smart contracts, mining issues, phishing, social media. We learned that if we have a vulnerability, we need to understand how to remedy it. We also know that if we have permissionless or permissioned, our approach may vary. We then discussed Hyperledger Fabric and the benefits of the blockchain itself, but also the main security enhancements. We then discussed Ethereum as well. And then we moved on to R3 Corda. I want to personally thank you for attending the course, and I wish you the very best luck in the future. Please do connect up on LinkedIn, YouTube, Medium, and Steemit. Happy blockchaining. Over and out.